Well, ladies and gentlemen, welcome back. We now proceed to the highlight of today's event, the 2025 ICCM Award Ceremony, where we'll witness the brilliance and achievements of the mathematical community. Well, first of all, please welcome the host of the award ceremony, Professor Bonghao Lian, Secretary General of the Congress, and Professor at Shanghai Institute for Mathematics and Interdisciplinary Sciences.
Good morning. Welcome to the 2025 ICCM Award Ceremony. It is my pleasure and honor to be your MC today. Every 3 years, we gather at the opening of this conference to bestow our highest honors upon those colleagues whose profound research has reshaped the landscape of modern mathematics. This ceremony is more than a celebration of individual brilliance. It is a vital bridge to the public, designed to illuminate the elegance and impact of our field. By spotlighting these extraordinary breakthroughs, we aim to ignite a spark in the next generation of thinkers, inviting them to bring their own talents to the noble pursuit of mathematical discoveries. We shall begin with a presentation of the ICCM Medal. Formerly known as the Morningside Medal of Mathematics, which was established at the first ICCM in Beijing in 1998, it was renamed the ICCM Medal in 2019. The prize is conferred to an individual under the age of 45 of Chinese descent for their groundbreaking and highly influential research in pure or applied mathematics. It is the highest award of the Triennial ICCM and is divided into gold and the silver levels. The award is conferred in 2 separate categories, pure and applied mathematics. The ICCM Gold Medal is widely considered to be the Fields Medal of China. This year, we have 3 outstanding gold medal recipients, 2 in pure mathematics and 1 in applied mathematics. The first 2025 ICCM Gold Medal of Mathematics goes to Professor Hong Wang of the Kurang Institute of Mathematical Sciences and the IHES. Hong Wang's groundbreaking contribution include major advances on the Fourier restriction problem, the Falconer distance set, and the Furstenberg set conjectures, and recent contribution towards solving the Kakeya set conjecture. Through her innovative applications of multilinear and polynomial partitioning methods, she has opened new pathways in modern analysis, demonstrating profound depth and exceptional originality. We are proud to recognize her exceptional impact on the field. Congratulations to Professor Wang.
Now please welcome Hong Wang to the stage to receive the award. And let us invite Xintan Yao, President of International Congress of Chinese Mathematicians and Chairman of the Shanghai Institute for Mathematics and Interdisciplinary Sciences Board of Governors, and Xin Chou, Party Secretary of Fudan University, to present the award. Now let's take a photo together. Thank you, Professor Yao and Cho. Please take your seats on stage. And for Professor Wang, may we invite you to share your acceptance remarks.
大家好，非常感谢 ICCM 组委会和 ICCM 数学奖的评审委员会的支持和肯定。这些年来，每年来到上海，1月份来到上海参加 ICCM 数学年会，都是一个非常美好的经历。 能够与来自世界各地的数学家进行交流和合作，还有与朋友们相聚。今年感觉非常荣幸能够获得这个奖，并且同时也祝贺一同获奖的邓玉和袁心义等诸位老师。另外我还想感谢一路走来遇到的各个老师的支持和引导，特别是我的博士导师 Larry Guth，他极有耐心的教我如何系统性的对科研课题进行思考，并且同时对很多领域保持活跃的热情和兴趣。我还想感谢这些年来遇到很多合作者，我们进行了很多的讨论和交流，尤其是我的合作者 Josh Zhao， 我们一起度过了很多艰难的困难，克服了很多艰难的事情，并且坚持到了最后论文完成。最后我想感谢我所有学习和工作过的单位、学校遇到的老师和同学们，还有非常热情友好的同事们，他们的专业一流，并且对我进行了很多的支持。谢谢大家。
Thank you, Professor Wang. Please join the audience. Congratulations.
The next 2025 ICCM Gold Medal of Mathematics goes to Professor Xinyi Yuan of Peking University. Xinyi Yuan's groundbreaking achievements, including his collaborative proof of the average Combes conjecture and his recent solution of the long-standing geometric Bogomolov conjecture, have resolved central problems in the field. Yuan's work, which offers powerful new tools for modern arithmetic geometry, as evidenced by his publications in the Annals of Mathematics, continues to shape the global mathematical landscape. We are honored to recognize his profound contribution in number theory. Congratulations to Professor Yuan.
Now please welcome Xinyi Yuan to the stage. And once again, we'd like to invite Professor Yao and Qiu to present the award. And now let's take a photo together. Thank you. Thank you, Professor Yao and Qiu. Please join the audience. For Professor Yuan, may we invite you to share your acceptance remarks.
大家好，我非常荣幸在今天获得这个华人数学家大会的金奖，非常感谢组委会对我的数学工作的认可，这个对我意义非凡。我还要感谢我的家人，我的亲戚朋友，这包括我的父母、我的岳父母、妻子、小孩儿。我还要感谢在数学之路上面遇到的很多帮助过我的人。这包括我的老师、我的同学、我的同行、我的同事，还有我的合作者们。1981年，我出生于湖北省麻城市的一个普通的农村家庭。我父母用他们这个无私的奉献，支持我走上了今天这个数学的职业之路。在过去这些年里面，我遇到了一些比较重大的这个选择，人生的十字路口，然后伴随着大环境带来的一些好的机遇，我觉得让我在这条路上走得更加顺利，或者说最终能走上数学研究的这条路。1995年我上初二的时候，因为对数学的喜爱，我开始学习数学竞赛。然后1年后，因为数学竞赛，我保送了黄冈中学。然后后面又因为数学竞赛，我保送了北京大学。2000年，我进入北京大学学习，遇到了很多志同道合的同学们。 我们相互讨论，相互鼓舞，最终一起走上了这个职业数学的道路。2003年，我去哥伦比亚大学读博士，遇到了我的导师张寿武老师，他对我在数学上面的成长的作用是不可替代的。2019年，我离开了美国的加州大学伯克利分校，回到北京大学工作。我刚回国的时候，我很担忧，我在回国之后是否还能保持在美国的时候的那种研究的水准。然后现在看来，在这几年我做出的工作中，我还是感觉比较满意的。我这个在研究上这几年是比较高产的，而且我做出这些结果的质量也不亚于我当时在美国做出的结果。当然，我还需要继续努力，争取做出更重要的成果。谢谢大家。
Thank you, Professor Yuan. Please join the audience. Congratulations again.
Next, the 2025 ICCM Gold Medal of Applied Mathematics goes to Professor Yu Deng of the University of Chicago. The pioneering research of Yu Deng on wave turbulence and the probabilistic analysis of nonlinear PDEs has greatly advanced the understanding of randomness and stability in complex systems. Combining analytical rigor with forward-looking vision, he has established himself as one of the most influential young mathematicians of his generations. We are proud to recognize his exceptional contribution to analysis and probability theory. Congratulations to Professor Deng.
Please welcome Yu Deng to the stage to receive the award. And we'd like to invite field medalist, foreign member of the Chinese Academy of Sciences, foreign member of the European Academy of Sciences, fellow of the Royal Society and professor at Tsinghua University, Culture Berka, and Kuei-Ling Ding, academician of Chinese Academy of Sciences, president of Shanghai Jiaotong University, to present the award. Let's seize the moment with a picture. Thank you, Professor Berger and Ding. Please join the audience. And Professor Deng, would you like to share some of your thoughts for now?
非常荣幸能够在获得这一次ICCM 的最高奖项，感谢大会的主办方和评委会对我工作的肯定，我还要感谢我的父母和家人，他们一直以来对我的支持和我的导师和合作者们多年来我提供的有用的建议和帮助。从2018年开始，当时我和我的合作者 Hanny 在芝加哥聊到wave turbulence， 然后后来在冬天的时候，我和我合作者Andrea Namo 的聊起这个 Schrödinger 方程的随机初值问题，然后后来他的学生于海天来到我所就职的USC 然后做我的博后。从那时候开始直到后来我们一起发展了这个随机初值问题的这个random tensor theory，包括后来我和 Hanny 一起证明了这个wave equation 的推导从短时间到长时间再到最近我们得出了这个 Boltzmann 方程长时间推导，包括这个流体极限等等属于这个谢伯第六问题的一系列结果。可以说这几年来，对我来说应该是一个非常难忘，也是非常美好的体验。那么最后呢，借此这次获奖机会，我想希望将来能够在数学道路上继续去探索更困难问题，去希望能够将来做出更好的结果。谢谢。
Thank you. Thank you, Professor Deng. Congratulations. And we'd like to thank all our distinguished award presenters. And please, another big round of applause to all 3 ICCM Gold Medal winners. 再次掌声，恭喜3位。
We next present the ICCM Silver Medal. This year, we have 5 excellent ICCM Silver Medal winners in mathematics. The first ICCM Silver Medal of Mathematics goes to Professor Zhou Lixu of the University of California at Los Angeles. Recent works of Zhou Lixu have profound influence on the study of stable homotopy groups of spheres, motivic homotopy theory, and equivariant topology. They have advanced our understanding of the smooth structure on higher dimensional spheres and the Cavalier invariant problem. Bridging classical topology with modern algebraic geometry, his visionary work continues to shape the landscape of topology. We are proud to recognize his transformative contribution to modern topology. Congratulations to Professor Xu.
Please welcome Zhou Lixu to the stage to receive the award. And we'd like to invite Professor Michael I. Jordan, member of the National Academy of Sciences, member of the National Academy of Engineering, member of the American Academy of Arts and Sciences, and professor of the University of California at Berkeley. Mr. Xianzhong Zhao, Vice President of Tongji University, to present the award. Now let's take a photo together. Thank you, Professor Jordan Zhao. Please join the audience. And Professor Xu, may we invite you to share your acceptance remarks.
首先，我想感谢世界华人数学家大会评奖委员会对我和我的合作者们的工作的认可。其次，我想感谢世界华人数学家大会对于我的研究领域拓扑学，尤其是代数拓扑学的认可。最后，我想感谢我一直以来学习和工作过的地方，感谢我的导师 Peter May， 感谢我的合作者们。 尤其是复旦大学的王国珍、复旦大学的林伟南，还有浙江大学的孔佳，感谢我的家人和朋友们对我一直以来的支持和鼓励，谢谢大家。
Thank you, Professor Xu. Please join the audience and congratulations again.
The next ICCM Silver Medal of Mathematics goes to Professor Yihang Zhu of Tsinghua University. The deep insights of Yihang Zhu's linking arithmetic geometry, automorphic representations, and the geometry of Shimura varieties, along with his pioneering research on the stabilization of trace formulas, have illuminated central problems and opened bold new directions. Zhu's leadership, scholarship exemplifies intellectual excellence and international leadership. We are honored to recognize his groundbreaking contribution to arithmetic geometry. Congratulations to Professor Zhu.
Please welcome Yihang Zhu to the stage. And we'd like to invite Ye Tian, academician of Chinese Academy of Sciences, professor of Academy of Mathematics and Systems Science at Chinese Academy of Sciences, and Shi Juntong, foreign member of Norwegian Academy of Science and Letters, academician of the Academy of Sciences of Latin America, and president of New York University, Shanghai, to present the award. Let's take a photo together. Thank you, Professor Tian and Tong. Please join the audience. Professor Zhu, may we invite you to share your acceptance remarks.
大家好。首先，我想感谢我的母校清华大学。在清华大学，我走入了数学的大门。其次，我想感谢我的导师Kissing 教授和我这些年来的合作者。我从他们身上学到了很好的数学，然后他们也成为了我探索数学的这个伙伴。 然后我想感谢我的家人这个多年的对我的包容和支持。然后最后我想和这个在座的学生和年轻的学者分享一句《论语》里面的话，就是古之学者为己，今之学者为人。我希望大家可以为自己来学习和研究数学。具体的说，就是我们要以数学的美和探索未知的乐趣为动力，来进行数学的学习和研究，而不用那么在意一些这个外在的这个评价或者这个他人的看法。谢谢。
Thank you, Professor Zhu. Please join the audience and congratulations.
The next ICCM Silver Medal of Mathematics goes to Professor Bang Tijin of the Chinese University of Hong Kong. The pioneering work of Bang Tijin at the interface of rigorous analysis and scientific computing, particularly in the inverse problems and computational imaging, has profoundly influenced the medical imaging, machine learning, and parameter identification. A leading figure in this field, Jin's scholarship, leadership, and mentorship exemplify the spirit of innovation and collaboration in modern science. We are proud to recognize his visionary research, which continues to transform computational mathematics and its application. Congratulations to Professor Jin.
Please welcome Bang Tijin to the stage. We'd like to invite Yiming Mok, academician of the Chinese Academy of Sciences, Vice President of the Hong Kong Academy of Sciences, Edmond and Peggy Te, Professor in Mathematics at the University of Hong Kong, and Yunchun Liu, President of Shanghai University of Finance and Economics, to present the award. Let's take a photo. Thank you, Professor Mark and Liu. Please join the audience. Professor Jin, may we invite you to share your acceptance remarks.
大家好，首先我要感谢这个评奖委员会，就是感谢他们认可我的工作。我在应用数学领域一些小的成绩。我取得这些成绩呢，实际上是跟许多人长期支持非常有关系。在我的研究生涯里面，我得到许多人的帮助。其中特别我要感谢我的博士生导师，香港中文大学周军教授，他的长期指导、鼓励，还有他的支持，塑造了我的研究生涯。其次呢，我要感谢我的许多合作者，我有大概100多个合作者。其中呢，我得特别感谢我的长期合作者，香港理工大学的周志教授，还有武汉大学的吕希亮教授。我的大部分研究成果都是与他们共同完成的。最后呢，我要感谢我的父母的无私奉献，还有我的太太李光莲博士她的长期支持和理解。谢谢大家。
Thank you, Professor Jin. Congratulations.
The next ICCM Silver Medal of Mathematics goes to Professor Huanchen Bao of the National University of Singapore. Huanchen Bao's works represent a unifying vision across algebra, geometry, and combinatorics, epitomized by his pioneering construction of canonical bases for quantum symmetric pairs. His work have reshaped the field and revealed deep structures connecting quantum groups and total positivity. Recognized internationally for his creativity, depth, and mathematical elegance, Bao is a rising leader whose ideas continue to illuminate the frontiers of modern algebra. We are proud to recognize his exceptional achievements. Congratulations to Professor Bao.
Please welcome Huanchen Bao to the stage. And we invite Wei Xiaoshen, academician of the Chinese Academy of Sciences, Dean of the School of Mathematical Sciences at Fudan University, and Chief Professor of the Shanghai Center for Mathematical Sciences at Fudan University, and Xiaofan Wang, President of Shanghai Institute of Technology and Vice Chairman of the Systems Engineering Society of China, to present the award. take a photo. Thank you, Professor Shannon Wang. Please join the audience. And for Professor Bao, may we invite you to share your acceptance remarks.
大家好，我非常荣幸能够获得这次的 ICCM 的银奖。首先我要感谢ICCM 大会对我工作的认可，并且授予我这份荣誉。我记得我第一次参加 ICCM 大会是在2018年，当时是在台北，当时我还是一个博后。当时我很荣幸也获得了最佳论文奖，对于当时的我是一个非常大的鼓励。现在又能够获得 ICCM 银奖，对我来说，更是一个莫大的鞭策。我真心的希望未来 ICCM 能够持续成为大家交流思想、建立联系的地方。谢谢大家，也再次感谢这份荣誉。
Thank you, Professor Bao. Congratulations.
The next ICCM Silver Medal of Mathematics goes to Professor Kelei Wang of Wuhan University. Kelei Wang's pioneering advances in phase separation and free boundary problems, including a novel proof of the savant's one-dimensional symmetry theorem, have resolved long-standing challenges and opened transformative directions in nonlinear analysis. Wang's deep insight and originality have greatly enriched our understanding of the mathematical structures of underlying physical phenomena. We're honored to recognize his distinguished scholarship, which continues to shape the field of analysis. Congratulations to Professor Wang.
Please welcome Kelei Wang to the stage. And we'll invite Chu Melissa Liu, Chair of the Department of Mathematics at Columbia University, and Professor Akito Futaki at Tsinghua University to present the award. Let's seize the moment with a group photo. Thank you, Professor Liu and Futaki. Please join the audience. And for Professor Wang, may we invite you to share your acceptance remarks.
首先感谢评奖委员会的认可，然后尤其是对我从事的这个椭圆 PDE 这方面的这个领域的这方面的工作的一些认可，然后我非常感谢，然后为我提名的几位老师，然后感谢我一路以来，然后遇到的各位老师，然后以及合作者，我从你们身上学到了很多。最后我想感谢我的家人，尤其我的妻子唐哲女士，然后谢谢她为我们家庭的付出，然后谢谢大家。
Thank you, Professor Wang. Congratulations. And now we move to the 2025 ICCM Special Prizes presentation. We will present several prizes named after outstanding mathematicians.
We shall now present the ICCM Chern Prize. In honor of Professor Shengsheng Chern, the ICCM Chern Prize, established in 2001, recognizes mathematicians and individuals of Chinese descent who have made enormous contributions to mathematical research or public service in mathematics development. This year, we are fortunate to have two ICCM Chern Prize winners. The first 2025 Chern Prize goes to Professor Ji Xiangfu of Fudan University. Ji Xiangfu's groundbreaking work on non-Kähler manifolds, particularly his collaboration with Xingtong Yao in solving the Strominger equations, has had a profound impact on the field. This achievement, resolving a 20-year-old open problem, has significantly advanced our understanding of non-Kähler geometry and its relevance in string theory. Fu's contribution to continue to inspire and shape the area of geometric analysis. Congratulations to Professor Fu.
Now let's welcome Ji Xiangfu to the stage to receive the prize. And we'd like to invite Xintan Yao and Kenji Fukaya, Professor of the Yao Mathematical Sciences Center at Tsinghua University and Professor at the Beijing Applied Mathematics Research Institute, to present the prize. Let's take a photo together. Thank you, Professor Yao and Fukaya. Please take your seats on stage. And for Professor Fu, may we invite you to share your acceptance remarks.
Thank you. Kenji.
作为一名几何工作者，能够获得应有陈信生先生肖像的奖牌，这是对我最高的奖励。感谢评奖委员会，感谢所有的合作者，感谢所有指导过我数学的老师们，特别是李军院士与邱成龙先生。最后呢，感谢我的家人们，谢谢大家。
Thank you, Professor Fu, and congratulations again.
The next 2025 ICCM Chen Prize goes to Professor Jinli Zhai of the University of Pennsylvania. Jinli Zhai has made significant contribution to the study of modular forms and abelian varieties. His influential research has deepened our understanding of the intricate relationship between number theory and algebraic geometry. A recipient of numerous accolades, including being named an academician of the Academia Sinica, Zhai's work continues to inspire new development in number theory. We are honored to recognize his exceptional impact on mathematics. Congratulations to Professor Zhai.
Now please welcome Jinli Zhai to the stage. And once again, we'd like to invite Professor Yao and Fukaya to present the prize. Now let's take a photo together. Thank you, Professor Yao and Fukaya. Please join the audience. Professor Zhai, please move over to share your acceptance remarks.
非常感谢这个陈省生奖评审委员会，我得这个奖是100%的意外，但是也同时感到非常荣幸。我想借这个机会呢，谢谢许多年来我的老师朋友。我想先说的是，第一个是我的几位启蒙老师，李白飞老师、林早阳老师、康明昌老师。之后呢，是我的博士导师 David Mumford， 以及我的第一位合作者Gerd Faltings， 以及我长时间的合作伙伴 Franz Oert。最后呢，我要借这个机会感谢我的牵手，我们44年以前的今天刚刚好，我们互相就是叫做相濡以沫。 我们一路走过这个人生，我极度感谢他对我多年来的支持，谢谢。
Thank you. Congratulations again. Please join the audience, Professor Zhai.
We now present the ICCM Hua Prize. The year 2025 is the inaugural year for the ICCM Hua Prize. In honor of the memory of Professor Luo Genghua, known as the father of modern mathematics in China, the Hua Prize is conferred to an individual who has made pioneering contributions to a field of mathematics. This year, we are fortunate to have two ICCM Hua Prize winners. The first 2025 ICCM Hua Prize goes to Professor Qiwang Shu of Brown University. Qiwang Shu's pioneering contributions, particularly the development of high-order methods for conservation laws and discontinuous Galerkin methods, have profoundly shaped modern computational fluid dynamics and applied mathematics. Combining deep theoretical insight with lasting practical impact, his work continues to be a cornerstone of the field. We are proud to recognize his exceptional contribution in applied mathematics. Congratulations to Professor Shu.
Please welcome Qiwang Shu to the stage to receive the prize. And we'd like to invite Professor Jun Li, Academician of the Chinese Academy of Sciences and Director of the Shanghai Center for Mathematical Sciences at Fudan University, and Andrei Losev, Professor at the Shanghai Institute for Mathematics and Interdisciplinary Sciences, to present the prize. Take a photo together. Thank you, Professor Li and Losev. Please take your seats on stage. Professor Shu, may we invite you to share your acceptance remarks.
非常高兴得到这个第一届的这个Prize，对我这个感谢这个评奖委员会对我这个常年在这个应用数学方面工作的一个肯定。我做的这些工作就是 over many years， 这是跟很多的合作者、学生一起完成的，所以呢，这个是一个集体的功劳。谢谢大家。
Thank you, Professor Shu. Please join the audience and congratulations.
The next 2025 ICCM Hua Prize goes to Professor Ziquan Luo of the Chinese University of Hong Kong, Shenzhen. Ziquan Luo's innovative work in optimization, big data analytics, and wireless communication has transformed both theory and practice. His data-driven network optimization framework, which integrates artificial intelligence with statistical modeling, has significantly improved global communication efficiency. Luo's exemplify a rare combination of rigorous research, impactful innovation, and visionary academic leadership. We are honored to recognize his groundbreaking achievements. Congratulations to Professor Luo.
Please welcome Ziquan Luo to the stage. And once again, we'd like to invite Professor Jun Li and Andrei Losev to present the prize. Let's take a photo together. Thank you, Professor Li and Losev. Kindly join the audience. Professor Luo, may we invite you to share your acceptance remarks.
Wow, what a surprise, actually. I'm greatly honored and actually surprised because I was surprised I was nominated, and I was even more surprised the committee actually selected me for this prize. Hua Luogeng was a household name for me when I grew up in China, so it's a great honor. There are a lot of people that I would like to thank, particularly Professor Chen Ming and Professor John Siklas, where I did my PhD at MIT. He was my PhD advisor. Professor Chen Ming was my academic mentor.
in Peking University, where I did mathematics as an undergraduate. I also like to thank my classmates, wonderful group of classmates at Beida. They really made my life at Peking University enjoyment and excitement. They are Professor like Zhu Yongchang, Wang Xuefeng, Wang Xiaoping, Yu Bing, many of them, okay. They made the study of mathematics and English great fun for me. I also like to thank my students, Sun Ruoyu, Mason Razavayayan, and also my postdocs, Yao Storm, and then Hong Mingyi. They had made such a wonderful from them. I would like to thank my collaborators, Paul Tsang, whom I collaborated for many years, wrote 23 papers together. And also I would like to thank Professor Yingli Ye, Professor Shu Zhongzhang, Stephen Boyd, and also Professor Dimitri Bertsikas, John Shipang. These are all my long-term collaborators. Thank them profoundly. They really shaped my scientific thinking and career path. Also, my collaborators include engineers from industry, especially Huawei, where I did my, I think the most challenging applied mathematics work using AI and mathematical models to optimize the practical wireless networks performance. It was very enjoyable journey and collaboration with them. I thank them profoundly. Last but not least, I thank my family members, my parents who gave me not only my life, but also courage and taught me how to be a good person. They set very high expectation for me. And then I know my father would have been very proud today if he had lived to the day to see this moment. And also, I would like to thank my family members, my two daughters, Christine and Charlene, and most importantly, my dear wife for 30 years, Jenny. Their love, their support has made my work so much of a joy, and also they have provided me with a cozy and welcoming home. They put up with my crazy hours, so this honor really belongs to them. Thank you.
Congratulations. Thank you, Professor Luo.
We now present the ICCM Lin Prize. The year 2025 is the inaugural year for the ICCM Lin Prize. To commemorate the great applied mathematician, Professor Jiaqiao Lin, the Lin Prize is awarded to an individual who has made transformative advancements in applied mathematics or mathematical sciences. The 2025 ICCM Lin Prize goes to Professor Weinan of Peking University. Weinan groundbreaking contribution to multi-scale modeling, high-dimensional numerical algorithms, and the mathematical foundations of machine learning have redefined the interface between theory and application. A scholar of profound depth, creativity, and influence across disciplines, Er's work continues to inspire new generations of researchers. We are proud to recognize his exceptional contributions and profound influence in mathematics. Congratulations to Professor Er.
Please welcome Weinan to the stage. And we'd like to invite Ye Tian, Academician of Chinese Academy of Sciences, Professor of Academy of Mathematics and System Science at Chinese Academy of Sciences, and Jianpan Wang, former president of East China Normal University and a member of the International Eurasian Academy of Sciences, to present the prize. let's seize the moment with some photos. Thank you, Professor Tian Wang. Please join the audience. Professor please come over and share your acceptance remarks.
今天的主角应该是3位金奖获得者，首先对他们表示祝贺。But I do have something else to say. First of all, I want to thank the prize committee for selecting me as the winner of the First Link Prize. I was trained in pure math, and I switched to applied math because I wanted my work to be directly useful, and that turned out to be very hard. I switched from one area to another, from numerical analysis to computational fluid dynamics, material science, chemistry, chemical engineering, many different fields. But for the longest time in my career, I did not think that my work was really useful. Finally, I was about to give up and try one last thing, which is machine learning and AI. Then a whole new world opened up. So looking back, machine learning was indeed the major missing pillar of applied mathematics. Applied math without machine learning is like pure math without analysis. In my 40 years of scientific career, I've almost always been an outlier. I was certainly very much an outlier in Princeton's math department. I've also been pretty much an outlier in the applied math community. I'm very grateful for my colleagues, particularly my colleagues in Princeton's math department, but also my colleagues in the applied math community for accommodating me and giving me the awards without having much idea about what I was doing. Especially in the Princeton math department, I don't think they have the slightest idea about what I was doing. But still, they accommodated me and give me enough room. When I finally figured out what I should be doing and thought that I can make some real contributions at Princeton, I had to leave. That will always be a regret in my scientific life. Thank you all for listening to these remarks. I also want to thank my teachers, students, friends, and my family for believing in me and supporting me throughout these years. Thank you all.
Thank you, Professor. Please join the audience and congratulations.
We now present the International Cooperation Award. The ICCM International Cooperation Award was established in 2004. 2 prizes have been named in honor of the great mathematicians John Coates and Wilfred Schmidt. The award recognizes individuals who have made significant contributions to the development of mathematics in China in collaborating, teaching, and supporting Chinese mathematicians. The 2025 ICCM Wilfred Schmidt International Cooperation Award goes to Professor Kocher Birkar of Tsinghua University. Kocher Birkar's most celebrated contribution lie in birational geometry, particularly the minimal model program. He co-founded the theory of complemented varieties, providing a powerful framework to study singularities and log canonical thresholds. His work with Hakon, McKiernan, and others established the finite generations of canonical rings in general dimension, a monumental result. For this, and for his profound proof of the Borisov-Alexeyev-Borisov conjecture on boundedness of Fano varieties, settling a key case of the BAB conjecture, he was awarded the Fields Medal in 2018. Birkar's research has fundamentally advanced the classification of algebraic varieties. Congratulations to Professor Birkar.
Please welcome Kocher Birkar to the stage. And we'd like to invite Wei Xiaoshen, Academician of Chinese Academy of Sciences, Dean of the School of Mathematical Sciences at Fudan University, and Chief Professor of the Shanghai Center for Mathematical Sciences at Fudan University, and Xijun Tong, Foreign Member of the Norwegian Academy of Science and Letters, Academician of the Academy of Sciences of Latin America, and President of New York University, Shanghai, to present the award. us take a photo together. And thank you very much, Professor Shen and Tong. Please join the audience. And Professor Birka, may we invite you to share your acceptance remarks.
Hello and good morning again. This is the third speech this morning, but it has been fun. First of all, it's a great honor to get this award. I would like to thank all the people involved, the committee members, and also those who nominated me for this. It's really a great honor. So I have been here in China for almost 5 years. That's 4.5 years. And I'm happy that more and more people are coming to China to teach or to study or simply to do research. So all we know that the mathematical community around the world is a connected community. We cannot separate the community in China and the rest of the world. The natural thing is that these communities are all very strongly connected to each other. To allow the flow of knowledge and also human resources to go outside, come inside, and so on. We all know the importance of this. And I hope that even more people come here to work, to study, and so on, because that is the natural thing to do, especially with the rapidly developing community, the scene of mathematics in China. That is very natural that more connections are made between China and the rest of the world. So just in my personal experience, in the last few years that I have been here, I have tried to train many young people, both students and also postdoctoral fellows, as well as some young faculty. And it has been very rewarding to work with these young people. And this, you could say, is one example of this international dimension of mathematical development in China. I have also been involved in developing a joint program with Imperial College. We have a joint postdoctoral program, and so far we have hired 5 fellows from 5 different countries. It cannot be more international than that. And hopefully this can be expanded to more countries, not only with the UK, but with other countries as well. And I'm sure that these kind of efforts will just continue and make the mathematics in China even more international. Thank you.
Thank you. Congratulations, Professor Birka.
Next, the 2025 ICCM John Coates International Cooperation Award goes to Professor Andrei Okunkov of Columbia University. Andrei Okunkov has made profound contribution in bridging probability theory, representation theory, and algebraic geometry as cited by the International Mathematical Union. His innovative techniques, including the use of random partitions and variational principles, have revolutionized the understanding of enumerative geometry, particularly through connections to Gromov-Witten and Donaldson-Thomas theories. Okunkov's research reveals deep, unexpected links between diverse mathematical disciplines, providing powerful new tools that continue to inspire significant advances across multiple fields. We are proud to honor his immense contribution to mathematics. Congratulations to Professor Okunkov.
Please welcome Andrei Okunkov to the stage. And we'll invite Yuval Paris, professor at Beijing Institute of Mathematical Sciences and Applications, member of U.S. National Academy of Sciences, and Zi Xinzhong, the executive dean of Zhizhen School of Interdisciplinary Mathematics at the Chinese University of Hong Kong, to present the award. Thank you, Professor Paris. And Joan, please join the audience. And Professor Okunkov, may we invite you to share your acceptance remarks.
尊敬的各位同事、老师们、同学们，大家好！非常感谢大会授予我国际合作奖。这个奖不只是我一个人的，也是所有帮助过我的朋友和同事的。数学要发展，离不开国际合作。多年来 ，ICCM 为世界各地的华人数学家提供了重要的平台。能在这里与大家互相学习，共同进步，我深感荣幸。最后，祝愿 ICCM 越来越好。也祝愿数学事业薪火相传，造福人类。谢谢大家。
谢谢公构教授。
We now present the ICCM Yang Prize. Inaugurated in 2022, the ICCM Yang Prize was established to commemorate Professor Luo Yang, who was a distinguished leader in mathematics, known for a lifetime of exceptional contribution and service to mathematics in China. This award recognizes leading researchers with distinguished achievements in mathematics. The 2025 ICCM Yang Prize goes to Professor Peng Shan of the Yao Mathematical Sciences Center at Tsinghua University. Peng Shan has established herself as a leading figure in geometric representation theory, particularly through her pioneering work on rational Ceremony algebras and quantum loop groups. Her research elegantly bridges categorical representations with the geometry of Fourier varieties, providing deep insights into the categorical SLN actions. By developing innovative categorical framework, she has solved long-standing conjectures influencing the study of modular representations and quantum groups globally. Her transformative work continues to inspire next generations of scholars in representation theory and beyond. Congratulations to Professor Shan.
Now please welcome Peng Shan to the stage. And we'd like to invite Professor Haizhong Li and Akito Futaki at Tsinghua University to present the award. Thank you, Professor Li and Futaki. Kindly join the audience. And Professor Shan, we invite you to share what you're thinking right now.
尊敬的邱先生、各位领导、各位来宾、各位老师、各位同学，大家上午好。这次获得这个奖项，我感到非常的荣幸，然后也感谢这个大会的评审委员会对我工作的肯定。我2017年底回国工作，到现在正好就是8年。我想借此机会感谢清华大学数学中心给我提供了一个稳定的、可以安心科研的工作环境。我觉得在这里我认识了很多有才华的，就是很多卓越的学者、有趣的灵魂和有才华的学生，然后对此我感到很幸运。我也感谢一路以来培养我的师长，还有前辈，然后还有我的同事跟朋友，然后他们让我在数学的旅程里获得了很多快乐。也感谢我的家人一直以来对我的支持，谢谢大家。
Congratulations, Professor Shan. And also a big round of applause to Professor Liam. Kindly join the audience. And once again, may we have another big round of applause to all of our winners. Thank you so much for your contribution in the mathematical community. Thank you. Well, this concludes the first half of ICCM award ceremony, and now we're moving on to the second half. We now begin the ICCM Best Paper Award ceremony. Please welcome Professor Chang Pan Mok from the Shanghai Institute of Mathematics and Interdisciplinary Sciences to host this part of award ceremony.
Good morning, ladies and gentlemen. It is my privilege to host the presentation of the 2025 ICCM Best Paper Award today. Established in 2017, the ICCM Best Paper Award recognizes outstanding mathematical research papers that demonstrate exceptional innovation, depth, and impact in the field. The award is divided into gold level and silver level. This year, a total of 14 papers have been selected to win the gold medal, while 20 papers have been selected to win the silver medal. We shall begin with the presentation of the Best Paper Gold Award. We shall divide the presentation into five groups of papers. The first three winners of the 2025 ICCM Best Paper Gold Award are the following papers. First, Algebraicity of High Green Functions at the CM Point, by Ying-Kung Li of the Max Planck Institute for Mathematics in Bonn. The author investigates the algebraic nature of the value of a high green function on an orthogonal Shimura variety at the single CM point and an analog of harmonic mass forms in the setting of Hilbert modular forms. He proves results concerning the arithmetic of the Fourier coefficients of their holomorphic part. Second, the Fontaine-Mason conjecture in the residually reducible case by Liu Peng of the University of Michigan. The author proves new cases of the Fontaine-Mason conjecture on two-dimensional Galois representation over Q, when the residual representation is reducible, and generalizes the work of Skinner-Wiles in the ordinary case. In addition, the author also treats the residually irreducible case and proves the Fontaine-Mason conjecture completely in the regular case when P is at least 5. Third, sharp bounds for multiplicities of Bianchi modular forms by Weibo Fu of Princeton University. The author proves a degree 1 saving bound for the dimension of the space of cohomological automorphic forms of fixed level and growing weight on SL2 over any number field that is not totally real, and establishes a sharp bound on the growth of cuspidal Bianchi modular forms. Furthermore, the author proves finite generation of Iwasawa modules under the assumption that microlocalization is generic, solving the representation theoretic question by estimating growth of Poincare-Birkhoff-Witt filtration on such modules. Congratulations to the winning authors.
Now please welcome Yikun Li, Liu Pan, and Weibo Fu to the stage. And we'd like to invite our award presenters, Chris Brav, Professor at Shanghai Institute for Mathematics and Interdisciplinary Sciences, Li Mingge, Professor at Academy of Mathematics and System Science of Chinese Academy of Sciences. All right, let's take a photo together. Let's stand closer. All right, thank you, Professor Brav and Ge. Kindly join the audience. And congratulations to our award winners. Congratulations again. Thank you.
The next three winners of the 2025 ICCM Best Paper Gold Award are the following papers. First, nonlinear inviscid damping near monotonic shear flows by Alexandru Ionescu of Princeton University and Hao Jia of the University of Minnesota, Twin Cities. The authors proved nonlinear asymptotic stability of a large class of monotonic shear flows among solutions of the two-dimensional Euler equations in a channel T cross the interval 1. If U is a solution which is a small and Gavre smooth perturbation of such a shear flow at time t equals 0, then the velocity field U converges strongly to a nearby shear flow as the time goes to infinity. This is the first nonlinear asymptotic stability result for Euler equations around general steady solutions for which the linearized flow cannot be explicitly solved. Second, nonlinear inviscid damping for a class of monotone shear flows in a finite channel by Nada Musmoudi and Wei Ran Zhao of New York University, Abu Dhabi. By using the wave operator of a slightly modified Rayleigh operator and well-chosen coordinate system, the authors proved the nonlinear inviscid damping for a class of monotone shear flows for the initial perturbation Gavre 1/x class with compact support. Third, panning for gold, Model X knockoffs for high-dimensional control variable selection by Emmanuel Candace of Stanford University, Yingying Fan of the University of Southern California, Lucas Janssen of Stanford University, and Jingqi Li of the University of Southern California. Many contemporary large-scale applications involve building interpretable models linking a large set of potential covariates to a response in a nonlinear fashion, such as when the response is binary. To address such a practical problem, the authors propose a new framework of Model X knockoffs, which reads from a different perspective the knockoff procedure originally designed for controlling the false discovery rate in linear models. Congratulations to the winning authors.
Now please welcome Hao Jia, Weiren Zhao, Yingying Fan, and Jingqi Liu to the stage. And for our award presenters, we'd like to invite Xiaochun Rong, professor at Rutgers University and Capital Normal University, Shenlong Luo, director of the Institute of Applied Mathematics at Chinese Academy of Sciences.恭喜各位，请大家一起合影留念。Let's take a photo together. Thank you, Professor Rong and Luo, and congratulations to all of our award winners. Please join the audience.
The next three winners of the 2025 ICCM Best Paper Gold Award are the following papers. First, Transfer Learning for High-Dimensional Linear Regression, Prediction, Estimation, and Minimax Optimality by Sai Li of Renmin University of China, T. Tony Tsai of the Wharton School, University of Pennsylvania, and Hongzhe Li of the University of Pennsylvania. The authors consider estimation and prediction of high-dimensional linear regression model in a transfer learning setting. This is accomplished by using samples from the target model, as well as auxiliary samples from different but possibly related regression models. When a set of informative auxiliary samples is known, an estimator and the predictor are proposed, and the optimality is established. Second, product structure and regularity theorem for totally non-negative flag varieties by Hao Chan Bao of the National University of Singapore and Xu Hua He of the University of Hong Kong. The authors introduce a new total positivity on the full flag variety of an arbitrary Kashmiri group, generalizing the ordinary total positivity. Combined with the generalized Poincare conjecture, they prove that the closure of each totally positive Richardson variety is a regular CW complex homeomorphic to a closed ball. Moreover, total positivity on the full flag provides model for the ordinary totally non-negative partial flag variety. As a consequence, they confirm the conjectures of Galashin, Karp, and Lamprou. Third, label false cycles and the K-pi1 conjecture for artin groups by Jingyin Huang of Ohio State University. The author shows that for a large class of artin groups with Dinkin diagrams being a tree, the K-pi1 conjecture holds, as well as for another class of artin groups whose Dinkin diagrams contain a cycle, which applies to some artin groups whose Dinkin diagrams are hyperbolic type. This is based on a new approach to the K-pi1 conjecture for artin groups. Congratulations to the winning authors.
Please welcome Tsai Li, T. Tony Tsai, Huanchen Bao, and Jingyin Huang to the stage. And we'd like to invite Qimen Xiao, Chair of the Department of Statistics and Data Science at Southern University of Science and Technology, and Bo Liu, Professor of School of Mathematical Sciences at East China Normal University, to present the awards. Let's stand closer for the group photo. Thank you, Professor Xiao and Liu, and congratulations to our award winners. Please join the audience. 谢谢各位。
The next two winners of the 2025 ICCM Best Paper Gold Award are the following papers. First, Infinite Many Lagrangian Fillings by Roger Cazos of the University of California at Davis and Honghao Gao of Tsinghua University. The authors proved that all maximal TB positive Lasandrian torus links NM in the standard contact 3 sphere, except for the families 2M, 3, 4, and 3, 5, emit infinite many Lagrangian fillings in a standard symplectic 4-ball. These imply that there exists Lagrangian concordance monoids with subgroups of exponential growth and yield Stein surfaces homotopic to 2-sphere with infinitely many distinct exact Lagrangian surfaces of high genus. They also show that there exists infinite many satellite and hyperbolic knots with Lasandrian representatives emitting infinite many exact Lagrangian fillings. Second, evolution of angular momentum and center of mass at no infinity by Po-Ning Chen of the University of California at Riverside, Jordan Keller of Harvard University, Mu-Tao Wang of Columbia University, Ye-Kai Wang of Taiwan Cheng Kung University, and Xingtong Yao of Harvard University. The authors study how conserved quantities such as angular momentum and center of mass evolve with respect to the retarded time at no infinity, which is described in terms of a Bondi-Sachs coordinate system. These evolution formulae complement the classical Bondi mass loss formula for gravitational radiation. They are further expressed in terms of the potentials of the shear and Lewis tensors. Congratulations to the winning authors.
Now please welcome Honghao Gao and Mu-Tao Wang to the stage. And we invite our award presenters, Yuan Longxing, Professor of School of Mathematical Sciences at Fudan University, Huan Yuguo, Director of Key Laboratory of Non-Linear Mathematical Models and Methods at Fudan University, Standing Committee Member of Shanghai Municipal Committee of the CPPCC. 祝贺各位数学家们，让我们一起合影留念。Thank you, Professor Xin and Guo, and congratulations to all of our award winners. Please join the audience. 谢谢各位，请入座。
Next three winners of the 2025 ICCM Best Paper Gold Award are the following papers. First, full derivation of the wave kinetic equation by Yu Ding of the University of Chicago and Zahad Hani of the University of Michigan. The authors confirm a main conjecture in the theory of the kinetic theory of nonlinear wave systems. The result is a wave analog of Landfort's theorem on the derivation of the Boltzmann kinetic equation from particle systems, where in both cases one takes the thermodynamic limit as the size of the system diverges to infinity, and as the interaction strength of waves or radius of particle vanishes to zero according to particular scaling law. Second, high-single wave formula for unitary groups, the non-singular terms, by Tony Feng of the University of California at Berkeley, Zhiwei Yun of the Massachusetts Institute of Technology, and Wei Zhang of the Massachusetts Institute of Technology. The authors construct special cycles on the moduli stack of Hermitian Stukas and prove an identity between the alt-central derivative of non-singular Fourier coefficients of a normalized Siegel-Eisenstein series and the degree of special cycles of virtual dimension 0 on the moduli stack of Hermitian Stukas with R lengths. This may be viewed as a function field analog of the Cutler-Rappaport conjecture. Third, a proof of the Cutler-Rappaport conjecture for Kramer models by Qiao He of Columbia University, Chao Li of Columbia University, Yousheng Shi of Zhejiang University, and Tonghai Yang of the University of Wisconsin-Madison. The authors proved the Cutler-Rappaport conjecture for Kramer models of unitary Rappaport zinc spaces at ramified places. It is a precise identity between arithmetic intersection numbers of special cycles on Kramer models and modified derived local densities of Hermitian forms. As an application, one can relax the local assumptions at ramified places in the arithmetic Siegel wave formula for unitary Shimura varieties. Congratulations to the winning authors.
Now please welcome Yu Deng, Tony Feng, Qiao He, and Yousheng Shi to the stage. And we'd like to invite our award presenters, Yuan Ke, Professor and Party Secretary and Vice Dean of the School of Mathematics at Renmin University, and Daqing Wang, Professor of University of California at Irvine, to present the awards.掌声祝贺各位获奖者，也请我们一起合影留念。Thank you, Professor Ge and Wang. Please join the audience, and also congratulations to our award winners. 谢谢各位，请入座。
We now present the ICCM Best Paper Silver Award. We shall divide the presentation into 4 groups of papers. The first 5 winners of the 2025 ICCM Best Paper Silver Award are the following papers. First, Logarithmic Riemann-Hilbert Correspondences for Rigid Varieties by Hangsheng Diao of Tsinghua University, Kaiwen Lan of University of Minnesota, Ruochan Liu of Peking University, and Xinwen Zhu of Stanford University. On any smooth algebraic variety of a p-adic local field, the authors construct a tensor functor from the category of de Rham p-adic état local systems to the category of filtered algebraic vector bundles with integrable connections satisfying the Griffiths transversality. As an application, the authors show that this p-adic Riemann-Hilbert functor is compatible with the classical 1 overall Shimura varieties for local systems attached to representations of the associated reductive and direct groups. Second, geometric Bogomolov conjecture arbitrary characteristics by Junyi Xie and Xingyi Yuan, Peking University. By using Yamaki's reduction theorem on the geometric Bogomolov conjecture and the Mani-Mumford conjecture proved by Renaud and Hrushkovsky, authors give a proof of the full geometric Bogomolov conjecture. Third, comptage the systems local elliptic sur le cube by Hongjie Yu of Chinese Academy of Sciences. The author gives a formula for the number of irreducible elliptic local systems with a fixed rank over the base chain to the addirect closure of a curve over the finite field FQ that are fixed by the Frobenius endomorphism, and proves that this number behaves like a Lefschetz fixed point formula for a variety of FQ. This generalizes a result of Drinfeld in rank 2 and proves a conjecture of Deligne. Fourth, convergence of uniform triangulations under the Cardi embedding by Nina Holden of New York University and Xin Sun of Peking University. The authors consider embedding planar maps into an equilateral triangle delta, which can be called a Cardi embedding. Under the Cardi embedding, the planar map induces a metric and an area measure on delta and a boundary measure on the boundary of delta. They proved that for uniformly sampled triangulations, the metric and the measures converge jointly in the scaling limit to the Brownian disk conformally embedded into delta. Fifth, the critical two-dimensional stochastic heat flow by Francesco Caravana of the University of Milano Bicocca, Rongfeng Sun of National University of Singapore, and Nico Ziguras of the University of Warwick. The authors considered directed polymers in random environments in the critical dimension d equal to 2, focusing on the intermediate disorder regime when the model undergoes a phase transition. They proved that at criticality, the diffusively rescaled random field of partition functions has a unique scaling limit. It's the natural candidate for the long-sought solution of the critical two-dimensional stochastic heat equation with multiplicative space-time white noise. Congratulations to the winning authors.
Please welcome Hansen Diao, Junyi Xie, Xingyi Yuan, Hongji Yu, Sun Xin, and Rongfeng Sun to the stage. And we'd like to invite Yi Li, Professor and Vice Chairman of the Board and Assistant Director of the Shanghai Institute for Mathematics and Interdisciplinary Sciences, Xiping Zhu, Professor at Sun Yat-sen University, and Yat-sun Pu, Professor of University of California at Riverside, to present the prizes.祝贺各位，请大家一起合影留念。Now let's take a photo together. Thank you, Professor Li, Zhu, and Poon, and congratulations to our award winners. Kindly join the audience. 谢谢各位，请入座。
The next 5 winners of 2025 ICCM Best Paper Silver Award are the following papers. First, Intersection Theorem Complexes in Positive Characteristics by Mao Xing of University of Science and Technology of China and Zebao Zhang of Chongqing University of Technology. The authors established a positive characteristic analog of intersection comotive theory for variations of Hart structure. As an application, they give an algebraic proof of the E1 degeneration theorem due to Katani, Kaplan-Schmidt, and Kashiwara-Kawai, and the vanishing theorem of Saito for variation of Hart structures of geometric origin. Second, quasi-map wall crossing for GIT quotients by Yang Zhou of Fudan University. author proves a wall-crossing formula for epsilon-stable quasi-maps to GIT quotients, conjectured by Chocang, Fontaine, and Kim, for all targets in all genera, including the orbital case. The author proves that stability conditions in adjacent chambers give equivalent invariance, provided both chambers stable. By using this, the author proves that the quasi-map J functions are on the Lagrangian cone of the Gromov-Witten theory. Third, finite volume hyperbolic three-manifolds are almost determined by their finite quotient groups by Yi Liu of Peking University. For any orientable finite volume hyperbolic three-manifold, the author proves that the profinite isomorphism type of the fundamental group uniquely determines the isomorphism type of the first integral cohomology as marked with the Thurston norm and the fiber classes. Moreover, up to finite ambiguity, the profinite isomorphism type determines the isomorphism type of the fundamental group among the class of finitely generated three-manifold groups. Fourth, exponential mixing of geodesic flows for geometrically finite hyperbolic manifolds with cusp by Jialun Li of Fudan University and the Laurent Schwartz Center for Mathematics and Wenyu Peng of the University of Chicago. The authors established exponential mixing of geodesic flow on the unit tangent bundle respect to the Bowen-Margulis-Sullivan measure for a geometrically finite discrete subgroup gamma in the identical component of the special orthogonal group with signature D+1,1 with parabolic elements. As an application, they obtain a resonant free region for the resolvent of the Laplacian on the space. Fifth, on ends of finite volume non-compact manifolds of non-positive curvature by Ran Ji of the Capital Normal University and Yunhui Wu of Tsinghua University. The authors confirm a Folk law conjecture which suggests that for a complete non-compact manifold M of finite volume with sectional curvature K between -1, 0, if the universal cover M is a visibility manifold, then the fundamental group of each end of M is almost nilpotent. Congratulations to the winning authors.
Please welcome Zebao Zhang, Yang Zhou, Yi Liu, Jialun Li, and Yunhui Wu to the stage. And we'd like to invite our press presenters. Zai Jiushang, Professor and Executive Vice Director of the Shanghai Institute for Mathematics and Interdisciplinary Sciences, Shen Jin Cheng, Professor at the Institute of Mathematics of Academia Sinica, and Mr. Zhigang Duan, General Manager of Shanghai Yangpu Science and Technology Innovation Group, to present the prizes.祝贺各位获奖者，大家一起合影留念。Thank you, Professor Xiang, Professor Cheng, and Mr. Duan. Kindly join the audience, and congratulations to our award winners. Please be seated. 谢谢各位，请入座。
The next 5 winners of 2025 ICCM Best Paper Silver Award are following papers. First, Stability of Euclidean 3-Space for the Positive Mass Theorem by Chonghang Dong of Stony Brook University and Antoine Song of California Institute of Technology. The authors show that the Euclidean 3-space is stable for the positive mass theorem. This confirms the conjecture of Huisken and Immanen. As an application, they also prove Bartnick's strict positivity conjecture. Second, the Frobenius structure theorem for affine log Calabi-Yau varieties containing a torus by Sean Keel of the University of Texas at Austin and Tony Yue Yu of California Institute of Technology. The authors prove a variant of Frobenius structure conjecture by Gross-Hacking Keel in mirror symmetry, and the spectrum of this algebra is supposed to give the hypothetical mirror family. They prove that the algebra generalizes and gives a direct geometric construction of the mirror algebra of Gross-Hacking Keel conservage. Several combinatorial conjecture of GHKK, as well as the positivity and Laurent phenomenon, follow readily from the geometric description. Third, matrix-valued Alenkine equation and the Keller-Rubinstein-Sternberg problem by Mingwen Fei of Anhui Normal University, Fanghua Lin of New York University, Wei Wang of Zhejiang University, and Zhifei Zhang of Peking University. The authors consider sharp interface limit of matrix-valued Alenkine equation. They show that the sharp interface system is a two-phase flow system. The interface evolves according to motion by mean curvature. In the two bulk phase region, the solution obeys the heat flow harmonic maps. On the interface, the phase matrix in two sides satisfy novel mixed boundary condition. Fourth, on L-infinity estimates for fully nonlinear partial differential equations by Bing Guo of Rutgers University and Duanghong Huang of Columbia University. The authors obtained sharp L-infinity estimates for general classes of fully nonlinear PDEs on non-Kähler manifolds. The method applies not just to compact Hermitian manifolds, but also to the Dirichlet problem, to open manifolds with a positive lower bound on the injectivity radii, to n-1 form equations, and even to non-integrable almost complex or symplectic manifolds. It is the first method applicable in any generality to large classes of nonlinear equations, and it usually improves on other methods when they happen to be available for specific equations. Fifth, a restriction estimate in R3 using brooms by Hong Wang of the Koran Institute of Material Sciences, New York University, and the IPS. If f is a function supported in truncated paraboloid in R3 and E is a corresponding extension operator, then the author proves that for all P larger than 3 plus 3 over 13, then the LP norm of EF is less than or equal to constant times the L-infinity norm of F. The proof combines Wolff's 2n arguments, polynomial partitioning techniques. The author also observes some geometric structures in wave packets. Congratulations to the winning authors.
Now please welcome Antoine Song, Tony Yue Yu, Wei Wang, Fanghua Lin, Bing Guo, and Hong Wang to the stage. And we invite our award presenters, Yuval Paris, professor at Beijing Applied Mathematics Research Institute, member of U.S. National Academy of Sciences, Xin Kang Inc., professor at Taiwan Tsinghua University, and Hua Xin Lin, professor of Shanghai Institute for Mathematics and Interdisciplinary Sciences. Congratulations. Let's take a photo together. Thank you, Professor Paris, Ing, and Lin. And also congratulations to our award winners. Please join the audience. 谢谢各位，请入座。
The next 5 winners of 2025 ICCM Best Paper Silver Award are the following papers. First, Global Axisymmetric Euler Flows with Rotation by Yang Guo and Benoit Posada of Brown University and Klaus Wittmeyer of the University of Zurich and the University of Vienna. The authors construct a class of global dynamical solutions to 3-dimensional Euler equations near the stationary state given by uniform rigid body rotation. These solutions are axisymmetric, of Sobolev regularity, have non-Lagrange world, and scatter linearly due to the dispersive effect induced by the rotation. Second, the Chow-T structure on the infinite category of motivic spectra by Tom Bachmann of the University of Mainz, Hanne Jiakong of Zhejiang University, Guozheng Wang of Fudan University, and Zhou Zhu of the University of California at Los Angeles. The authors define the Chow-T structure on the infinite category of motivic spectra over an arbitrary base field K. They identify the heart of certain T structure when the exponential characteristics of K is inverted. Restricting the cellular subcategory, they identify child heart as certain category of even graded comodules. Furthermore, they show that the infinite category of modules over the child truncated sphere spectrum is algebraic. Third, the existence of Zariski dense orbits for endomorphisms of projective surfaces by Junyi Xie of Peking University. Let F be a dominant endomorphism of a smooth projective surface of an algebraic closed field of characteristic 0. The author proves that if there's no non-constant invariant rational function under F, then there exists a closed point whose orbit under F is Zariski dense. This result gives a positive answer to the Zariski dense orbit conjecture for endomorphisms of smooth projective surfaces. Fourth, Bessel F isocrystals for reductive groups by Dazin Xu of the Chinese Academy of Sciences and Xinwen Zhu of Stanford University. The authors construct the Frobenius structure on a rigid connection on multiplicative group GM for a split reductive group G-check introduced by Franco Gross. These data form a G-check valued over convergent F isocrystal, which is the p-adic companion of the Klustermann G-check local system constructed by Heinhoff, Go, Yun. Fifth, canonical bases arising from quantum symmetric pairs of Kashmuri type by Huang Chen Bao of National University of Singapore and Wei Qiang Wang of the University of Virginia. The authors prove a conjecture of Balagovich-Kolb, removing a major technical assumption in the theory of quantum symmetric pairs. Even for quantum symmetric pairs of finite type, the new approach simplifies and strengthens the integrality of quasi-K matrix and the construction of one canonical basis by avoiding a case-by-case rank-1 analysis and removing the strong constraints on the parameters in a previous work. Congratulations to the winning authors.
Now please welcome Yan Guo, Hannah Jia Kong, Guo Zhen Wang, Zhou Xu, Jun Yixie, Daxin Xu, and Huan Chenbao. And also we'd like to invite our award presenters, Professor Zhongling Wu from the Beijing Institute of Mathematical Sciences and Applications, Yao Mathematical Sciences Center of Tsinghua University, Professor Thomas Biton and Professor Wen Wei Lin from Shanghai Institute of Mathematics and Interdisciplinary Sciences.祝贺各位，请大家一起合影留念。Congratulations! Let's take a photo together. Thank you, Professor Wu, Biton, and Lin, and also all of our award winners. Congratulations again. Please join the audience. Thank you. 谢谢各位，请入座。Same time, a big round of applause to Professor Mark. Thank you. Please join the audience. 再次邀请大家把最热烈的掌声送给我们今天所有的获奖者。同时呢，也要再次对全球各地的华人数学家们致以最崇高的敬意。无论得奖与否，你们都是华人之光。Well, now this concludes the 2025 ICCM Award Ceremony. Thank you very much for being here with us. Enjoy your lunch and have a lovely day.
We are honored today to have Professor Andrei Akunkov of Columbia University speaking to us. Professor Akunkov received the Fields Medal in 2006, particularly for his work in enumerative geometry and relations to mathematical physics. Today, he was granted the John Coates International Cooperation Award. He is a foreign member of the Chinese Academy of Sciences and a member of the US National Academy of Sciences. We are very glad and honored to have him tell us today about stable envelopes for critical loci.
Thank you, Chris, for this very kind invitation. So I'm going to report on a joint work with Yalong, Yahao, and Zijun. And here you can see a picture of us more or less in the alphabetical C-O-Z-Z order, and taking a break from our critical thinking. And so from our team, there will be 2 talks. And so on Wednesday, Yalong, who is the first here, he will give a more technical discussion of what is it we actually do, and mine will be more of a bird's eye view of the subject. So our project is about interaction between 2 areas, namely is about geometric representation theory and how it interacts with enumerative geometry. Well, enumerative geometry also, which is also very close to certain parts of mathematical physics. And what is geometric representation theory? So representation theory is the study of how can a group or an algebra act usually by matrices. If you find matrices are not enough, maybe you consider operators between some spaces, maybe operators between some function spaces. Correspondence is similar. Correspondence, if you have two spaces, that the correspondence is basically just a subvarizing the product of those. The same way as a distribution of the product of 2 spaces induces a linear operator between functions. So with some technical assumptions, so none of the technical assumptions will be made too explicit in this talk. A correspondence between 2 spaces x and y induces a map. Well, for us, it's not a map on functions, but rather a map between certain cohomology theories one associates with these spaces. And this could be any kind of cohomology theory you want. Could be ordinary cohomology, could be equivariant cohomology, could be equivariant K theory, etc., etc. And this is all of those flavors are very much used and explored in geometric representation theory. But for us, the setting for us is what's called critical cohomology or critical K theory. And I'll give a more formal definition of what it is later. But this critical cohomology or critical K theory is associated to a function W on a smooth space X, and what it measures is the singularities of that function. And so this critical, well, we're not the first, certainly not by far not the first to study critical cohomology groups, and also in relation to geometric representation theory. And it's already clear that these critical cohomology groups are extremely versatile and very, very ubiquitous in many both theoretical and applied contexts. And one can ask why? Why is this? What's the reason for their versatility and their ubiquity? And as a mathematical physicist, I will answer this question for you in my own preferred way. Namely, I will draw upon the role, the physical origins of these notions and the role and the role the function, etc., plays there in this physical origins. So from its very, very beginning, when representation theory started, it has always had very, very fruitful interactions with theoretical physics, and you can. So if you look at the picture of atomic orbitals, what you really see is a basis in representations of the group of rotation. There's a trivial representation, then there's a three-dimensional representation, there's a five-dimensional representation, seven-dimensional representation, and so on. And you diagonalize a certain operator that has a basis. This gives you a basis in this representation. Those are the states of an electron in the potential, and so that's your picture. When the states of the physical system, they're really labeled by vectors in representation of some, in this case, Lie group. So group of rotation in 3 space, it's a Lie group. So it's a finite dimensional group. So quantum groups, and whenever I say quantum groups today, what I'm really referring are more, people would say quantum loop groups. That is to say, they're not just deformation of a finite dimensional Lie algebra of a finite dimensional group, they're deformations of functions of one variable with values in a group, or functions of one variable with values in an algebra. So it's already infinite dimensional object. And those arose historically, those arose in the study of, so quantum mechanics, you can imagine quantum mechanics as being physics in one dimension, namely just the time, and then maybe some finitely many degrees of freedom. And then the next level is two-dimensional, or one space, one time dimension. And in the study of exactly solvable physics in 1 + 1 dimension, it's that the quantum groups arose. And they're also really, so now of course the system is much bigger, but also the group is much bigger. It's not a finite dimensional group, it's a group that already, like functions of one variables with values in a group, so it's a group's much bigger, space is much bigger, representation is much bigger, but still, it is the case that vectors in representation of a group really label the states of a quantum system. And this was, of course, a huge success, and rapidly followed by applications of quantum groups all over other areas of mathematics. Low-dimensional topology, etc., and even percolated to my own field, geometry, mathematical physics. But what is maybe surprising from, well, I don't know, maybe some other people will find it not surprising, but certain kinds of quantum groups, and now even bigger kind of quantum groups, they also find application in quantum theories of more dimensions. So in many numbers of dimensions. And when but then of course they describe not all of physical states. We no longer label all states of the quantum system. We label quantum group representation appear in a very, very, you can say, some people would say very, very small fraction of what the physical, somehow the whole variety of physical problem is. Or maybe some people will find it to be maybe the most important. And of course, the phenomena you find, the theories we study are basically some version of supersymmetric gauge theory in some number of dimensions. And the main phenomena we find are instanton-like objects that are, so instantons were originally studied in 4-dimensional gauge theory. Instanton is something, the name means, instant means in 4-dimensional space time, so it's some kind of codimension 4 bump. So in higher dimensions, so in dimension 6, that will be still codimension 4 thing, so it'll be something which is now by itself 2-dimensional, etc., etc. And I don't know how to draw an instanton, but when I need to illustrate the word instanton with a picture, I usually borrow this picture by Tufte. And so you can, but what it really means to illustrate is an instanton is really a four-dimensional object, and it also has like a matrix degrees of freedom, which I don't know, maybe you can imagine. But what is easy to plot is a close analog of this instantons. You can call them instantons are like this at the expense of maybe being misunderstood. You can consider these objects to be you can call these objects to be like a billion instantons, although maybe it makes no sense to other people. And so, or rather, you can say the instantons are matrix analog or vector analogs of this object. So very, very closely related to instantons in four dimensions are the Hilbert scheme of points in C2. And what's the Hilbert scheme of points? It's an algebraic variety that describes all possible positions of points in either complex plane or, so complex plane is the same as four-dimensional real space, but it also describes how these points come together and form a more general zero-dimensional subscheme of C2 is after all an algebraic variety. It can have a zero-dimensional subschemes, and so when points come together, you remember from which directions they came. And so that is easy to visualize and easy to plot. So when the points gather, they gather in the ways that remember how they got together. And so, and moduli space of instantons are just direct analogs of that. And so Hilbert scheme of points in C2, that's an example of something called an Nakajima variety. And modular space of instantons are also Nakajima varieties. And understanding the quantum cohomology of the Hilbert scheme of points was a crucial building block for enumerative geometry of curves in all algebraic threefolds. And so what is a quantum cohomology? So since I not even described what the ordinary cohomology is, so maybe let me imagine you already know what the cohomology is. So quantum cohomology has to do with curves in your space. It's like something that it's about enumerative geometry of curves in your space. You say how in the moduli of curves in your space, how various things intersect. And why this has to do with complex threefolds? Because imagine, so this is a picture of points in complex plane. If I have a curve in this space, this is if I see this curve means this ball starts moving. So I get if I think about that movie, this will be that whole movie will be a curve in a threefold. So if you want to understand curve. If you want to understand curves in threefolds, that is very, very closely related to curves in Hilbert scheme of points. And so this is this been understood for. So this has been understood for a while. And to contrast what we do in our project with that old story, the similarly like a poster boy example of what we do is instead of Hilbert scheme of points in a plane, the simplest, maybe the most, maybe not the simplest, but maybe the simplest meaningful example, or not, maybe not. But anyhow, like the best, if you want to have one example of what we do in our papers is take the Hilbert scheme of points in a plane and replace it by the Hilbert scheme of points in space. Describe, and by analogy, if we want to bring that kind of movie metaphor, that means that the study of the Hilbert scheme of points in three space will hopefully eventually play similarly central role in understanding the normative geometry of Calabi-Yau fourfolds. And so so that's the that's the difference between what was known before and what we can do now. So, as I was trying to say before, now the quantum group computations, they're not previously in this electron orbitals examples or spin chain examples. Quantum group described the group, some kind of symmetry group, described all states of the quantum system. Now we're doing much more modest thing. We just describe certain indices, or instead of the whole operator, we compute maybe homology of some operator that squares to 0. But anyhow, that's a very fruitful setup, and the way to set it up properly, what we really compute are certain indices happen in certain related 2+1 dimensional theories. This could be in that theory you have some space which you can imagine as a Riemann surface, call it C. Then you have the time direction, and then you have some internal degrees of freedom, and this internal degrees of freedom could be really, really infinite dimensional, since we're really talking about some theories in more than 3 dimensions, so that this internal degrees of freedom can package, this internal degree of freedom can be really infinite dimensional spaces, but it's okay. And so what we want to compute is there's some evolution operator, so when we follow the arrow of time, we want to close it, but close not to itself, but maybe up to some symmetry G, which may act both, so G may act both on space, so the arrow of time doesn't exactly close, but close up to this symmetry G, and G also transforms the internal degree of freedom, and so you have this operator time and G. Well, I guess in my slide, somehow G goes in the wrong direction. I hope you forgive me. So this is you compose. I should have noticed, but anyhow, so you compose the evolution in time and the action of G, and then you don't really trace it, but you trace it. You take your spaces as Z2 graded. It's like an Euler characteristic. You compute the trace in the even part minus the trace in the odd part, just like the Euler characteristic. So this is this index is like a trace of, or the index is a virtual representation of the entire group of symmetries to which G belong, and like I said, they can act both on the physical two-dimensional space and all fields of the theory also, and we would like to compute that. And this is what we can so this is, I mean, this is maybe a physical version of what we're trying to compute. A mathematical version of that is you have some moduli spaces of maps, and then we'll get to that in a second, and then you compute the index of some virtual Dirac operator on this moduli spaces. And in this computation, when you compute, one great feature of the index is that index is not changed under any kind of continuous deformation. And so instead of looking at the so we're free to compute it in any of the point that we can access by continuous deformation. And in particular, we can imagine that our space is very, very big. That is to say, we look in the infrared limit. So C is a very, very, very big space. And it's enough to consider only those states that in this infrared, near each point of space, the system is in some vacuum state, and that state is described by some parameters, and these parameters define a map from your space C to the moduli space of vacuum of your theory. So the analogy, not just an analogy, but even an example of what I'm talking about. So imagine when we talk about like we'll talk about the air, right? So air is a very, very complex system, as you know, composed out of literally zillions of molecules that undergo extremely chaotic behavior. But when we talk about air, we refer to this room has some temperature, the next room has some temperature, outside there's some temperature, in a different city there's some temperature. That means at every place on Earth, the air is in some ground state, in some equilibrium. The parameter, that is, air is extremely complicated system, but it finds itself in some equilibrium state at near every point on Earth. And the parameters of that, equilibrium state, that is to say temperature, pressure, wind direction, that's enough for the air, but other substances might have other parameters. This vary from point to point. And so when I describe this kind of modulated vacuum, I mean that the system is in such state that at near each point of a curve is described, it's in some vacuum state or ground state, whose parameters are described by some function of the point C. And just to somehow reinforce this analogy, what I'm talking about, this modulated vacuum is a map from your space to the moduli spaces of vacuum. And an example of that map is really the map, namely the weather map. If you look at the weather map, that is really an example of that, namely for each point on Earth, which is, you can imagine your two-dimensional space. There is it records the temperature and the pressure and maybe the wind direction. So we already got ourselves that the problem becomes, in some sense, count all maps from some surface C to some space X. But in a second that this counting problem will become ever more specific, because in our supersymmetric situation, we do supersymmetric theories, only supersymmetric states contribute, and for us, the way this works, these maps have to be. So first, we set it up so that the space C is a Riemann surface, the space X is some algebraic variety, more or less, we'll get to that in a second. And the maps are holomorphic, so that becomes holomorphic maps from a Riemann surface to something that's a countable union of finite dimensional varieties. And on that countable union of finite dimensional varieties, we study something like the virtual index of Dirac operator. So that's the actual thing we study. And remains to say what kind of object is X. So what is X, and what does it mean to have a holomorphic map to X? And X, I said it's the moduli spaces of vacuum. So for instance, as I said, for air, that would be just for air in the frame where it's at rest, that would be just parameterized by density and the temperature and the pressure. So density, temperature, and pressure, that's enough. And so to be in a vacuum state means to be solution to some variational problem. Like for a system like air, means to be minimizer of a free energy, or some other thing. So this is being a vacuum is always modular space of solution to some variational problem. In our supersymmetric setting, that variational problem includes in particular the absolute value of derivative of some function term, namely the same function W that I already had at the beginning. And the vacuum will be just really the critical locus of that function. So we have a function, a holomorphic function, and its critical locus, that is the vacuum. This is the space of vacuum. And where does this function W live? Well, it lives in, where it can live? There's some pretty good guesses what it is. And so there's some vector space modulo some group. And so that's we take this. So we take this as our model. We take some vector space modulo some group so it's like the constant values. So the constant values of the matter field modulo gauge transformation. And so it's a linear representation of some group which I assume to be reductive. We take that quotient stack, we look at that stable locus inside, and the map to this critical locus. Well, that's just the map to the ambient stack that is generically length in this generical lines in X. It's a very simple definition. And these maps have a moduli that are countable union of algebraic varieties. And what's important is that, and this is already where this critical theory shows its flexibility, is that in this setup there is a very good theory of this virtual index of Dirac operator, or its cohomological version, the virtual fundamental class. And it spans, the construction of these things has a long history in algebraic geometry, and but maybe one thing I want to say that even in this setting, working with the critical locus of a function really offers some technical benefits. So this is even at this level, it's really it's really very convenient. So and this setup one can further refine by saying, so if I have this, I'm studying maps from my space to this moduli space of vacuum. So it's a map from a holomorphic map from a Riemann surface to some x, which is the critical locus of some function on some stack. I can further refine this counts by making insertion, that is to require my map to take a certain value at a certain point, and more generally, one can refine the map to land in some element of the critical K-theory. Now we finally get the definition of what is the critical K-theory. So if I have a function on a space, then if I look at the level set of this function, which is singular, that means, so let's assume that all my singularities appear at where the function takes 0, so it's the inverse image of 0 that's the singular fiber of my function W. And being singular means that there's the difference between the K-theory of coherent shifts and the K-theory of perfect complexes. So they're different, and but one maps naturally to the other, and by definition, the critical K-theory is the quotient of this. So that's exactly this exactly measures, the shifts, the coherent shifts on your space, which are do not have a fine free resolution. They're not perfect. So this is when we talk about quantum critical cohomology, quantum critical K-theory, what we do is we have some space which is X, and to which we associate this group, this critical K-theory group, and then on this critical K-theory group we have these new operations that have to do with counting curves that map to X and take given values at given points. So that's okay. So it's these indices that we want to compute. We want to compute using some new geometrically constructed quantum groups. And like I was saying, this goes quite a bit beyond the case of Nakajima varieties and similar varieties that was treated in the same general spirit that we already understand maps to things like Nakajima varieties. So there's a big literature from which I quoted a few authors here. And I want to, before we describe what kind of answer do we get, maybe I want to say again one word or two about finding justification for what we do. And of course, in mathematics, one doesn't really need to justify as long as we get interesting results and they're useful for something, well, you know, we satisfy that's justification enough. But you can still ask, this is going through this rather elaborate construction. What do you actually learn in terms of kind of like everyday mathematics? And of course, where is everyday mathematics and where mathematics of the future? That frontier moves all the time, but let's imagine that we kind of look back at what I said before about quantum groups and say, what can we, from this new perspective, how can we use it in the old setup? In the old setup, when people studied 1 + 1 dimensional problems, they understood so first of all, the problem so I told you that quantum group helps you construct an eigenbasis of your evolution operator in the space of your system. I was maybe not 100% truthful there because in complete generality, people didn't really know how to write down. So there's this procedure called beta ansatz. Of course, many people other than Hans Bethe contributed to that, and it starts by writing ansatz. Ansatz means you look for eigenvectors in a certain form, and then they really become eigenvectors when this in just general form some parameters satisfy some equations, and this beta eigen or this form, this maybe people say off-shell beta eigenfunction. And more general expressions of this off-shell function, there's a more general thing, namely the solution of some very important equation called the quantum Knižnik-Zamolodchikov equation, introduced by Frankel Rashetikhin. So those things were very well understood in examples, but in general, even I would say there wasn't such a great understanding of how to write these eigenfunctions or how to write the solutions of quantum Knižnik-Zamolodchikov equations in the generality in which they're defined. And it is the advantage of the geometric approach that we're pursuing here is that anytime you have a geometric realization of all these quantities, anytime you have a geometric realization of Knižnik-Zamolodchikov equation, for instance, you immediately have an integral solution to that equation. And you immediately have the off-shell beta functions and so forth. So that's even looking back to what people did almost 50 years ago, there's some improvement in what we do. And specifically, one improvement that people may appreciate over the old story with Nakajima quiver varieties, and is that the in Nakajima quiver variety starts with a quiver, and that quiver, well, it's not exactly the Dynkin diagram of the quantum group you're going to eventually construct, but it's sort of a little bit like the Dynkin diagram, and that in particular means that you take this Dynkin diagram in particular. There's no place for any arrows in that diagram, so you're not going to construct anything which is symmetrizable but not symmetric. There's no place for odd nodes in this diagram, so in particular, you're not going to construct supergroups. And there's some other feature of this quantum loop groups, and that they can be shifted. And I'll get to that, what shifted means. This again, you're not going to construct a shifted group from Nakajima quiver varieties. And in this setting, you can do all of that, and so all of that gets somehow very natural. So, but what is a quantum group? So, of course, I've been talking about quantum group for a while now, and I want to say that of course many people would have different opinion on what is a quantum group, and there's one school of thought is that quantum group is something you define by generators and relations, and that of course represented by the giants of the field, starting with Chevalier and ending with Greenfield and Jimba, and Not that I want to dispute anything with the giants of the field, but I personally always feel that defining an algebra by generating relations, it's perfectly fine, but it's a little bit like insisting that I'm going to define an algebraic variety by explicit equations. And some algebraic varieties have some good equations, but most algebraic varieties you describe by other means. You not describe them by equations. And so there's an alternative approach using what's called the R matrix, and this is this approach. Technical, of course, it goes from before the paper I'm going to mention in a second, but the paper, it is cited, but it's not really cited so much in representation theory literature, more in knot theory literature. So in the first issue of the first volume of the St. Petersburg Journal of Mathematics, there is a paper by Reshetikhin, Fadeev, and Takhtajan that explain how to define a quantum group using the R matrix in the case of classical groups. So they do it for for general linear and orthogonal and classical groups. And since this R matrix approach, this is very, very closely related to like in classical invariant theory. You understand that classical groups, they have a very special place in terms of classical invariant theory. But then in the second issue of the first volume of St. Petersburg Journal, there is a solo paper by Reshetikhin, and then he explains how to construct a quantum group like for general R matrix. So and usually people, not to subtract anything from the great contribution of Fadeev, Reshetikhin, and Takhtajan, and but usually people cite the FRT paper and forget about Reshetikhin's paper. But Reshetikhin's paper is very good reading, and it says how to really reconstruct the quantum groups from just the braiding, just the R matrix, and no further. So what's an R matrix? An R matrix is something which originated again in 1+1 dimensional quantum field theories, where it either described local weights in the vertex model or described scattering in particles with rapidities u and u prime respectively. And these particles carry certain degrees of freedom, certain internal degrees of freedom, which are labeled by take values in some space v and v prime. So when two particles scatter, there's some operator from the tensor product of v and v prime to the tensor product of v and v prime. And the key point about this operator, so either by miracle or by construction, and in this case of stable envelope, it's going to be by construction, they satisfy the Yang-Baxter equation. Namely, if you apply these operators, if you compose these operators, three of those operators in two different ways, you get the same result. So that's the in the Simon Center for Geometry and Physics, they have this most important equation of the world, and then there's E equals mc squared, but also, of course, they have the Yang-Baxter equation. So what's Reshetikhin? What is Reshetikhin saying? Is if you want the operators of the quantum group, just take arbitrary matrix element in one of the spaces. So if you have an operator in a tensor product, in one of the spaces you take an matrix element, then in the other space you get an operator. And this would be your operator of your quantum group. And that operator depends on the so since the R has a functional variable in it, that operator will be like an element of a quantum loop group. It will depend on the variable. So those are your operators. And this is why my G hat has hat on it. So there's some functional variable in it. And now if you look at these two diagrams, then they say that you can either take matrix elements in the tensor product of two representation, and that would correspond to composing the operators, or the other way around, you can take your physical space to be the tensor product and take matrix element in the auxiliary space, and that will define a coproduct. Right? So this means coproduct means you had one element of your algebra, you want to make 2 out of it. Well, that's very easy. You take the same matrix element, but now in the tensor product. That gives you a coproduct. And this tautologically, the coproduct and coproduct agree. And so once we have this R matrices satisfying the Young-Baxter equation, as Professor Rashidikhin explains, we do get a quantum group automatically. And so, in the geometric construction of quantum groups, this R matrix is the solution of the Young-Baxter equations. They're constructed using something called stable envelopes. Now, finally, I come to what is a stable envelope. So, the word stable comes from how this word is used in dynamics. So there's in dynamics, people study stable and unstable manifolds, or attracting repelling manifolds. It's an extremely useful notion in many areas of mathematics. If you have some action of a group or one parameter group of automorphism, you can study those points that have a limit. So imagine my flow all goes up here in this picture, and I look at those points that have a limit as time goes to infinity. So I have a collection of pairs, some point x, and its possible limit x naught. And then since this x naught is a limit of sigma of t applied to x as t goes to plus infinity, that x naught by itself is fixed. So this attracting set of pairs x and its limit x naught is naturally a submanifold in the product of my space and the fixed locus of sigma. So in other words, we started by saying that a correspondence between two spaces is a subvariety or submanifold or any kind of such object on the product of two spaces. And so that's okay, here it is. And like I said, this is extremely useful notion. And for instance, many people study whole algebras of various kinds, and whole algebras are this kind of things. You have to do with this sort of things on the moduli spaces of sheaves. But in general, the basic fact, and this is again, anybody who studies whatever that has to do with this sort of question, they realize that the basic feature of this attracting manifold is that they're not closed, because you can have some points in X such that they have a limit at both negative infinity and positive infinity, so that you have some trajectory that go from one fixed point to another. That is to say, as you follow your attracting manifold, in its closure could be another fixed point. So the attracting manifold, like I said, just the basic feature, nothing too fancy about it. Basic things about this stable manifold is that it's not closed. And so as is, it cannot be used as at least it cannot be used as a correspondence going from the fixed locus to the ambient space, because it doesn't map it the right way. So this is and what stable envelopes do is that they complete this attracting manifold to certain canonical correspondence between the fixed locus and the ambient space. And so this is in a certain canonical and maybe not too obvious a way. So for example, we don't take the closure, or if you just take the closure, that's usually just the wrong thing. But anyhow, the word stable envelopes means that they kind of like a stable manifold. An envelope means it adds certain lower corrections. So it kind of envelops in that sense, envelops the stable manifold, and that defines a correspondence. And well, I'm not going to give you definition, but I will say that with this definition, the uniqueness is obvious. But the existence, that's kind of delicate. And again, the setting of I keep saying that I'm not going into any technical details in this talk, but this is another place where the setting of critical homology, that's really feels like it's like the right setting for this sort of constructions because for instance, it's very simple to observe that to construct anyhow, certain parts of the construction still delicate, but at least certain parts of the construction they go along for the ride for free somehow. It really feels like just on kind of a hand-waving level. Literally feels like the critical cohomology is really the right setting for this sort of constructions. And but still, we need to make some assumptions, and there was on the previous slide, there were some assumptions that I made on self-duality. So there was some representation, some linear representation of some group, and I say, well, in fact, it's already very, very interesting to assume it's a quiver representation. But about that quiver, we have to make a certain self-duality assumptions for this stable envelopes to exist. And of course, we need to assume that the flow sigma of t preserves this self-duality and the function w. And what the stable envelopes do, so you think of this, the stable envelope is giving you 1/2 of the R matrix. So you think that the R matrix is, if you think the R matrix is a scattering of particles, they first the particles come in and they form some interacting bound state, and then they fly apart. And it's this part that starts from a fixed locus is something maybe simpler, and the ambient space is something more interesting. It's like the particles that are asymptotically free come and interact. So you go from a fixed locus to the ambient space. That's the way stable envelope works. That's like the half of the R matrix. And the other half is just the transpose operator. So that's or the transpose, and the transpose operator for stable envelope is just the other way around. You just change the role of infinities, plus to minus. And so that is how we construct the quantum group. And the way stable envelopes, the way the definition of stable envelopes works is it's really designed to be applied in the situation when you're going to use it to prove some rigidity. And very often, rigidity in enumerative. So, it's hard to talk about the complexity of enumerative computation to people who never tried one. Usually when people, I'm not to criticize anybody, but usually when people think, enumerative geometry is complex, they think Schubert calculus, and they think Schubert calculus is complex. Well, there's like nothing with the kind of enumerative computation we really do these days. Schubert calculus is just not remotely close in complexity. Okay. So this is the and very often it's really the only way to manage this complexity is to prove that something is zero or a constant. and this very often you do by rigidity argument. So this is, and if you want just like a baby example to try, has no curves in it, but even if you just try to pair, just to intersect the stable envelopes with unstable envelopes, if you just try to do it geometrically, that is really, really hard. But if you use the rigidity argument, then you see they form a dual basis, and that is, and then you immediately know that this must be something really good going about them, because if you just, for instance, if you just took the attracting manifold, you took its closure, like there's no way it will intersect with the opposite closure to form a dual pair of bases. And one place where we this rigidity argument really comes to the center stage is in geometric realization of the quantum equation. That equation, the cosmological equation, is different for quantum old 1+1 dimensional world. and we find it has a geometric meaning as a certain shift operator. And to prove that, we really use the rigidity argument, and the role it plays is really cornerstone in that it connects something, shift operator, that's something defined in terms of enumerative geometry that has curves in it, has some enumerative geometry going on, and so that really expresses some enumerative quantities in terms of a quantum group quantity. So that's really kind of the key step, the key bridge out of this. And a few kind of final remark. I said when I was listing the features of the quantum groups we find, one of them was the shifted business. And what is a shifted quantum group is so this R matrix is a function of one argument. And in the classical story, the value of this function at both 0 and infinity takes values, first of all, finite, and second, invertible. So it takes values in GL. This is kind of usual assumption, and this also what one finds for Nakajima varieties. And then what one finds in this generality, that of course is absolutely not true. And then what we find is that there'll be some. There'll be some shift, and shift refers to the fact that this function can have a zero pole or either have a pole or be non-invertible. That's the shift in the quantum group. So what we find, so like I said, we describe some kind of quantum operation, the critical cohomology of many varieties, and in particular for HILP C3, we write out specific formulas that describe the quantum critical cohomology of HILP C3, and I don't know. There's some maybe it was. I guess it was expected by us at the beginning that this would be, in fact, not so different from the formulas for HILP C2, except in kind of the same quantum group in a different representation. But the shift in particular came into, so it's not the same formulas. It's a shifted analog of the same it's a shifted version of the formulas for HILP C2. And the quantum group in question, if you want an example, that's a Yangian of something called GL1 hat. So this is GL1 hat by itself are loops into GL1, and then so Yangian is another loop, so it's a double loop groups, and then of course in general, of course, many much bigger groups appear. So to summarize, it was my intention in this talk to offer you kind of like a bird's eye view of a sequence of kind of long papers. And so the first one is already on the archive. You can download and read it. And you will find there, hopefully you'll find there are many advances there, but certainly we also leave many questions open, and you can both learn from what we know or answer questions we don't know. And for a more detailed discussion of what's going on in the project, I hope everybody will come to the lecture by Yalong, which is, yesterday when I look in the schedule, it said Wednesday at 11. I don't know if is it. Hopefully, it's the same. I don't want to mislead you, so you check the schedule. Anyhow, with this, I'd like to conclude my remarks, and thank you all for your attention. Mm-hmm. Also, so this is, it's not surprising that you get this kind of multiple loop groups. So already because you really, we're really talking about physics in many, many dimensions. So this is the fact that you get dependence, functional dependence on many variables. It's not particularly surprising. And in fact, already, if you want to do kind of like the old world, if you want to do the Hilbert scheme of points on a plane, you do it with double loops into GL1. If you want to do Hilbert scheme of points on some other surface, you're going to do double loops maybe in, not some other. If you want to do like ADE surface, you're going to, if you do Hilbert scheme of points on the ADE surface, then you'll find something like double loops into respective thing. But if you want to do some more complicated surface, like the Hilbert scheme of points on like a K3 surface, already there you find you get triple loop groups, and that's not my work, but it's yeah. So Sam DeHorty and other people, they've been exploring this sort of thing, and as you go into more general complicated geometry, you get this really unwieldy groups. You get things which are not just not finely generated. Their number of generators in each degree grow exponentially. That's just really wild. But like I said, it makes sense because we were talking about, even though we look at a small corner what is physics in so many dimensions, but that corner by itself is already enormous. So that's you get groups which are really of enormous size. But thankfully, so just to emphasize, this kind of Rashatikian approach doesn't require you to know all the generators and relations to write them down. You characterize the R matrix and you're done. You don't really need to list all the generators and relations.
Any more questions? If not, let's thank Professor Okunkov again.
喂，对。各位嘉宾，目前监修10分钟，10分钟后请回来。
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, The event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
Okay, we shall have the second talk, which will be given by Professor Hong Wang from ITS and NYU. So she is a great expert on harmonic analysis, which is a subject I'm always interested in. In the old days, I was very close friend with Charles Pfefferman, who worked on harmonic analysis under Stein, Bill Stein, and we have been discussing about, well, the similar problem that she has been working on, except in lower dimension. I thought it was difficult and interesting, and I thought there's not that much progress until I saw the recent works by Hong Wang and all his friends. I think it has been a spectacular achievement, and I feel that harmonic analysis will play a very important role in geometric analysis, a subject that I have been always interested in to develop. And I believe this will open up a new development in mathematics, and I'm very happy to have that Hong Wang getting an award for this year's ICCM, and her topic would be restrictions theorems and projection theorems. Thank you.
Thank you very much for the invitation and for the introduction. It's a great honor to come to ICCM and give this plenary talk. 因为在场的有外国友人，所以我可能还是用英文讲。So I will keep my talk in English. So today I'm going to talk about restriction theory and projection theorems. So as you can see, there are several boxes, and the conjectures or theorems inside the green box belongs to restriction theory, and the theorems estimates in the blue boxes belong to projection theorems, and the arrows highlight their connections. So as you can see, there's a lot of connections between the two fields, and I'm going to introduce the basic notions and theorems or conjectures in both fields, and try to give you some idea of how they are related. So let's start with restriction theory. So restriction theory studies the following function. Suppose the Fourier transform of a function f is supported on some submanifold M. As we will see, those submanifolds M are usually quite simple. Usually it's like, for example, we'll see in example 0 when M is a hyperplane, or example 1 when M is a paraboloid. Then what can we say about this function f? So more specifically, what can we say about the LP norm of the function? So the first example is, suppose the Fourier transform of a function is supported on the hyperplane, let's say the last coordinate equals to 0. Then our function f, capital Fx, can be written as integral of e to the 2 pi ix dot product with c0 times FCDC. So this yellow part is where the Fourier support of F. Then we can see that this function capital F is invariant under changing the last coordinate. So fxn equals to fx0. This implies that as long as f is non-zero, then the LP norm of f is infinity because it's invariant on the last coordinate, and then the last coordinate we integrate it to infinity. So this example 0 shows that the problem is not that interesting or is not well defined if M is a hyperplane. And the problem becomes more interesting when M is curved. So here is our second, example 1 means that we finally start to have some interesting example when the Fourier transform of F is supported on a paraboloid, this green shape. And such function is closely related to PDE. Such function is the linear solution to the Schrodinger equation. And then there is another example of, let's say the Fourier transform of F is supported on the moment curve, t squared on t cubed to t to the n. So such function is related to the exponential sums appeared in number theory. So the central open problem in restriction theory is Eli Stein's restriction conjecture, where he posed in the 60s. The restriction conjecture says that if the Fourier transform of function f is supported on some paraboloid, that is example 1, then for any p greater than 2n over n minus 1, where n is the dimension of the space, the LP norm of our function is bounded by a constant only depending on p and n times the Fourier transform of times the LP norm of its Fourier transform. So here we estimate the LP norm on the paraboloid. So it's an n minus 1 dimensional integral. Here the critical exponent 2n over n minus 1 comes from the example that the Fourier transform of f equals to 1 on the paraboloid. So Stein's restriction conjecture has been studied by many well-known mathematicians. We have, for example, Charlie Pfefferman, Eli Stein, Jean Bourgain, Tom Wolfe, Terry Tao, Vargas, and more recently by Larry Guth, and also as we will see later in the joint work with Shukun Wu. So the restriction conjecture is closely connected to many other conjectures. For example, it implies the Kakeya set conjecture, which is a conjecture in geometric measure theory. Towards the end of the talk, you will see that Kakeya conjecture can be reformulated as a special case of the more general problems we consider in projection theory. So the Kakeya set conjecture states that so a Kakeya set K is a subset of Rn that contains a unit line segment in every direction. Then the Kakeya set conjecture states that the Hausdorff dimension of K equals to the dimension of the space. So what it means is that any Kakeya set in Rn should be relatively large in the sense that it has 4 dimensions. Although it was proved by Beskovich that any Kakeya set in Rn could have a 0 measure. And the Kakeya set conjecture is important because if it's not true, then a lot of other conjectures will be false. For example, there is a very difficult conjecture called the Montgomery's conjecture on large values of Dirichlet polynomials. And this conjecture, if true, implies the Kakeya set conjecture in all dimensions. So how is restriction conjecture how does restriction conjecture imply the Kakeya set conjecture? So I hope this is a way to explain how restriction theory is connected to projection theory. So the restriction conjecture was, in the study of restriction conjecture, Jean Bourgain discovered in the 90s that one can perform a wave packet decomposition that relates the geometry to the study of waves. So what does wave packet decomposition mean is that previously we integrate the function in the whole space. Now we can take a large ball of radius r, and then we could imagine our r goes to infinity, so this large ball will approximate the whole space. So it makes sense to study the function in a large ball of radius r. Then in this large ball, the wave packet decomposition says that there exists a set of tubes of radius r, of radius r to the 1/2 and length r, and the function f can be decomposed as sum over ft, where t is a tube in our set. And if each ft is called a wave packet, so each such ft is a relatively simple wave in the sense that it is essentially supported on the tube, the long skinny tube, and its absolute value is essentially a constant on t. So if we ignore the oscillation, just consider the absolute value of each wave packet ft, then it's a rather simple function. It's like some constant times the characteristic function of the tube t. So here is the picture illustrating how the Fourier transform of f is connected to f and how the wave packet decomposition is like. So we know that if for the restriction conjecture, we study Fourier transform, we study functions with Fourier transform supported on the paraboloid. So on the right-hand side, we can see a paraboloid, which is the support of f, the Fourier transform of f, the f hat. Then we can decompose the support into some small caps of radius r to the -1/2. And each cap is associated to some wave packets, those tubes on the left-hand side, pointing in the normal direction of the hat, of the cap. For example, we can see this purple cap, and then on the left-hand side, there are three purple wave packets oscillating, and whose direction of those tubes, the support of the wave packets, pointing in the normal direction of this purple cap. And then for the blue cap, we can see one blue wave packet pointing this way, and then for the red small cap in the bottom, there are two red oscillating wave packets pointing up. So the Fourier transform is a way to decompose a complicated function into sum over simple waves. So for this particular function that we care about, the Fourier transform of the function is supported of paraboloid, then this wave packet decomposition says that f is sum over those ft supported on this long skinny tubes on the left-hand side. We can see that in some places, there are not too many tubes passing through a point. So at those places, for example, in some places there is only one tube passing through it. In those places, one can imagine the function to be relatively small. And in the middle, there are a lot of wave tubes passing through them, and one has to sort of understand how the oscillation will make the sum of wave packets large. So in some sense, this decomposing into this wave packet decomposition sort of have decomposed the study of those functions into tubes overlap. And we can imagine that in the places where there's not too many tubes overlapping, then the function is such that there are lots of wave packets passing through. And at the places where are lots of wave packets passing through, we need to understand the oscillation between the wave packets. So to summarize this page, an important ingredient to understand or to try to solve the restriction conjecture is to study how the tubes overlap. And this is the key object of study in the Kakia set conjecture. I hope I have I explained the basic setup and the problem we care about. So let's do some warm-up question. So let theta be of direction in the unit, so just any direction and in the unit disk, in the unit circle. Let's just consider the planar case. And we consider pi theta to be the orthogonal projection from R2 to R. So what does it mean is that, for example, and we have several directions. We have two directions, theta 1 and theta 2. So pi theta of theta 1. So we can see that the orthogonal projection image, pi theta 1 of E, are the yellow point. And similarly, for another direction, theta 2, pi theta 2 is the orthogonal projection of those white points E to the blue line in the direction of theta 2. So pi theta 2 of E are given a set of directions and a subset of R2, so those E, can we find a direction in our set lambda of directions such that the Hausdorff dimension of the orthogonal projection image of E is large? So in other words, let's see, we have those white points E, two directions, but let's imagine there are many. So can we find one of those directions, like one of those lines, such that the are large, many? So this question, to answer this question, there is a classical theorem by Marström, so that is Marström's projection theorem, which says that for almost every direction, the Hausdorff dimension. So this is the best possible because since we are projecting to a line in this warm-up scenario, then a line has dimension 1, so it cannot exceed the dimension of the line. So 1 is the best possible. In other words, those yellow points cannot be more than those white points. So the Hausdorff dimension of pi theta of E cannot be more than the Hausdorff dimension of E. So really, the conclusion of the Marsh assumption says that for almost every theta, for almost every direction. So what happens when we don't have that many directions? So what happens when the set of directions lambda is small? So Jean Bourgain had made an important discovery. He showed in 20, orthogonal projection image has dimension always greater, strictly larger than half of the Hausdorff dimension of the original set. So the statement is as follows. So suppose the Hausdorff dimension, suppose lambda is a set of directions in the unit circle, and E is a subset of the plane, and both of them have Hausdorff dimension, have positive Hausdorff dimension. Then there exists some epsilon greater than 0. This epsilon is implicit and usually extremely small, like 10 to the minus 10 or even smaller. And there exists an epsilon greater than 0 and theta in a direction, theta in our set of directions lambda, such that the Hausdorff dimension of the projection image is strictly greater than the Hausdorff dimension of E over 2 plus epsilon. So this theorem is very significant because it tells us the difference between real numbers and complex numbers. Why this is the case? So if we, in the statement of Bourgain's projection theorem, if we replace R2 by C2, the two-dimensional complex space, and S1 by the corresponding CP1, then this is no longer true because we can take E to be a subset of C2, which is R2, and lambda to be S1, which is a subset of CP1. Then for any theta for any direction theta in lambda, pi theta of E is just R. So the Hausdorff dimension of R is the Hausdorff dimension of R2 over 2, which is also the Hausdorff dimension of C over 2. So in the complex case, this statement is not true for any epsilon greater than 0. So since we said that previously Borgen's proof the epsilon is implicit and extremely small, then what is the best possible epsilon? So this question was only answered very recently. So the the optimal estimate we could have is the follows. The Hausdorff dimension of the orthogonal projection image is greater or equal than the minimum of the Hausdorff dimension of E, and the Hausdorff dimension of E plus the Hausdorff dimension of lambda over 2 and 1. So notice that what's the difference between this sharp bound and Marstrom's projection theorem? So because for Marstrom's projection theorem, lambda is like the entire circle, almost the entire circle, so the dimension of lambda is 1. Now in the general case, lambda could be extremely small but positive dimensional. So we have to add the middle term, the Hausdorff dimension of E plus the Hausdorff dimension of lambda over 2 there, so that the statement is true. And this result is sharp via some lattice example. So on this, the optimal bound for epsilon was conjectured. So the last yellow box is the optimal bound, and it was conjectured by Oberlin in 2012, and was proved by jointly with opponent Schmerkin and also Kevin Ren in 2023 as a special case of the Furstenberg set conjecture that we are going to discuss in the end. So we had the warm-up for the projection theory in R2 in the planar case. So the general setup, for the general setup, the problem become much more difficult and interesting, and it has closer connection to restriction theory. So the general setup is that now we have an m-dimensional subspace V of Rn. We consider pi V to be the orthogonal projection from Rn to V. Now the question is, given a set of m-dimensional subspaces in Rn and a subset of E of Rn, can we find a subspace V such that the Hausdorff dimension of the orthogonal projection image is large? Again, similar to Marstrom's result, we have a result by Mattila in 1975. For almost every m-dimensional subspace in Rn, we have the optimal orthogonal projection result. That is, the Hausdorff dimension of pi V of E equals to the minimum of Hausdorff dimension of E and M. Again, we would like to ask the following question. So Mattila's theorem, even though the bound is optimal, but the assumption is too strong in the sense that we need almost every m-dimensional subspace. So what happens if you only have a small collection of m-dimensional subspace? So if lambda is a tiny, very small subset of the Grassmannian the collection of m-dimensional subspaces in Rn. So the first observation is that it depends on the curvature of lambda. So again, previously when we talk about restriction theory, we talk about curvature because the problem only becomes interesting when the Fourier support has curvature. So for the projection problem in high dimensions, we face something similar in the sense that when we have curvature, the problem becomes more interesting. So here is an example that's sort of similar to the previous example 0 when the function has Fourier transform supported on hyperplane. So this example in projection theory says the following. So let L be a line in R3, so this, like this purple line. And lambda, now what is lambda? We take, so this example, we take M to be 1, so we are doing orthogonal projection to lines. And now the lambda, the set of directions, is the two plane that's perpendicular to L, intersecting the sphere, the two-dimensional sphere. So in this picture, the lambda is this, this great circle that's perpendicular to the purple line L. Then if our set E is containing L, then for any, so for example, if the set E, those white points on the second picture on the right-hand side, if E is containing L, then for any theta in lambda, pi theta of E is just this, this point in the middle. So the orthogonal projection, if E is contained in L, then the orthogonal projection to the line in direction theta is just 1 point. So the Hausdorff dimension of pi theta of E equals to 0, because the Hausdorff dimension of a point is 0. Then Fastler and Opponen asked the following question in 2013. What happens if lambda is away from the gray circle? So let's just say lambda is a smooth C2 curve away from any gray circle. For instance, let's say lambda is just this small circle that's on the last picture. So here is the theorem. When the short answer is when lambda is some curve that's, let's say C2 curve that's away from the gray circle, then we have the best possible orthogonal projection bound. So the conclusion is in the yellow box, and notice that the right-hand side of the yellow box is the previous Mathematicians result. That is the best possible. And also here, instead of, for Mathematicians result, we need to have almost every m-dimensional subspace, but here we only need a curve of m-dimensional subspaces, a one-dimensional curve of m-dimensional subspaces. So the statement is as follows. So for this result, the special case when n equals to 3 and m equals to 1 was proved by Pramanik, Yang, and Zhao. And when n equals to 3, m equals 2 was proved jointly with Gan, Guo, Guth, Terry Harris, and Dominique Maldac. And the general case for all dimensions for all n and m was proved joint with Shenwen Gan and Shaoming Guo. So the statement of the theorem is as follows. Let gamma be a non-degenerate curve in Rn. For instance, gamma could be the moment curve that we have seen before, like gamma t equals to t, comma t squared, comma t cubed till t to the n. And for any dimension m between 1 and m minus 1, and for any t in 0, 1, we can define the orthogonal projection pt from Rn to the span of the first mth derivative of gamma t. Then we know that for any Borel subset of E of Rn, and for almost every t, we have the best possible orthogonal projection image bound. So this restricted projection theorem, as we will see soon, that it is naturally naturally related to restriction theory, and it has many applications. So it has applications to homogeneous dynamics. So let's take a moment and see how this restricted projection theorem, or the proof idea, is related to free analysis. So this method is called a high-low method. So it was originally we found introduced by Roth in 1951 in a paper about the Herborn triangle problem in combinatorics, and then we joined with Guth and Noam Solomon. We rediscover or reintroduce it in 2018, and later we developed this further in the solution to the local smoothing conjecture for the wave equations. So this method is quite simple to start with, but very soon we'll see that we need a powerful tool from restriction theory to make good use of it. So for simplicity, let's just consider the case when m equals to 1. That is when we project two lines. Now PT, the orthogonal projection, is really simple. It's just x maps to the line in direction gamma prime t. So this that is those white points. We just do orthogonal projection to the line, to those yellow line in direction gamma prime t. So how to do it? We let delta to be a very tiny small scale, and that is, by the way, how we try to understand the different sets or shapes in geometric in this type of geometric measure theory. We approximate the set by a union of delta balls. So let's say E is a set of delta balls contained in the unit ball. Then we want to understand the orthogonal projection image of E to the line, to the white line in direction gamma prime t. So for example, in this picture, so I drew this picture in 3D to illustrate the difference between plane and higher dimensional cases. So those, let's imagine those white points are in three-dimensional space. Then what are the orthogonal projection image to the yellow line? So those are the orthogonal projection image are the yellow points. And how do we know where to take those yellow points? The way to do it is that we cover the set by delta times 1 slabs S that is orthogonal to the line gamma in direction gamma prime t. So we cover the set E by those yellow slabs. And in this picture, we cover it by 3 slabs. We can cover our E by 3 slabs. So the orthogonal projection image are just 3 points each of them correspond to a slab S. And so through this picture, we can see that the orthogonal projection image is exactly like the number of delta intervals in the orthogonal projection image is exactly the number of delta times 1 slabs needed in normal to the direction gamma prime t needed to cover our set E. So we have this key observation, although very simple. The orthogonal projection image is equals to the set of slabs required to cover our E in a given direction. And how do we estimate the quantity in this yellow box? The way to do it is to use some, first we start with some simple observation. So let phi s be a smooth bound function on S. So usually we could take, like say, the characteristic function, but here we are going to do some Fourier transform. So it's better if the function is smoother than the characteristic function. So we take phi s to be smooth bound functions on S. And let our f be sum over directions, and then sum over the slabs in those directions required to cover E and time of the smooth bound functions S. Then by double counting, the integral of f in S is roughly the volume of E times the number of slabs passing through each point. Since everything is delta separated and each delta separated t denote one direction, So at each point, there are delta to the -1 many slabs passing through it. And that is why we have the first first approximate equality. So we need to study the integral of f on E. And how do we do it is we do Holder's inequality and raise it to estimate the LP norm of f. And if we hopefully we can eventually bound the LP norm of f by something of the in terms of the number of slabs. And this will eventually imply that the number of slabs is large, and which means that the orthogonal projection image is large. So that is the goal. So what happens in the ... is the most difficult part. But so how do we study that most difficult part? We are going to use some Fourier analysis. Since phi s, so again, as before, f is the sum over smooth bump functions on each slab s. And when we use the Fourier transform, we want to study the Fourier transform for s, which is sum over the Fourier transform of phi s. So each phi s is just a smooth bump function on the slab. So the Fourier transform is also very easy. That is, so this yellow slab is the support of phi s, and then the Fourier transform of phi s is essentially supported on this yellow tube on the bottom. So that has length delta to the -1 and radius 1. And now, previously we know that the Fourier transform for f is the sum over the Fourier transform of phi s. And each phi s has Fourier transform supported on the tube pointing in the direction gamma prime t. So suppose s is orthogonal to gamma prime t, then the Fourier transform phi s points in the direction of gamma prime t. And then as t varies, the direction gamma prime t also varies. So this means that the Fourier transform of f is supported on the union of those tubes. And that is exactly where we use the fact that gamma prime t is away from the big circle. And then then the union of those directions in gamma prime t will form like a curved cone shape. And this is where we can use restriction theory. So previously, at the beginning, we said that restriction theory studies when the Fourier transform of a function is supported on some curved shape. And we need this gamma prime t to be away from the great circle to guarantee that the support of the Fourier transform of f is on some curved cone. I hope this picture in the orange box tells you how to apply restriction theory to study this projection problem. And then the projection theorem we proved has application to homogeneous dynamics and number theory. One can check the work of Lyndon Strauss, Mohammadi, Zhirong Wang, and Lei Yang. So for now, we studied how restriction theory could be applied to study projection problems. Now, for the rest of the time, we are going to study the opposite direction. The second observation is that if the set of m-dimensional subspaces, the collection lacks curvature, but E is away from, so when it lacks curvature, it might have some obstruction. But if E is away from any obstruction, then we still expect to have some good estimate on the dimension of the orthogonal projection image. Indeed, the Kakeya set conjecture is a special case of this observation. So for the rest, we are going to see, so first of all, since Kakeya set conjecture is closely related to restriction conjecture. So we are going to somehow use the ideas in projection theory to think about the chi-ket set conjecture and eventually hopefully relate to the restriction conjecture. So how is the chi-ket set conjecture a special case of this second observation? Again, this is a quite simple connection. For most of the line segments in m-dimensional space, we could parameterize by numbers in R2n, R2n minus 1. So this, let's say A and B are in Rm minus 1, then LAB is just the line that connects A, 0 and B, 1. And now suppose we have a subset E, we have a E that is a subset of R2n minus 1. Then this gives us a collection of lines LAB with AB containing E. So this K, as previously we used K to denote the chi-ket set. Now here K is a union of lines. Eventually it will look like some chi-ket set. So for now it's more general. K is a union of those line segments parameterized by points in E. And for the last picture, we are going to define some orthogonal projection PT. So the way we define this is so that the orthogonal projection image is those blue points is going to be equal to the union of lines K intersect with the hyperplane of height T. So indeed this projection image is, this orthogonal projection is very simple. PT is orthogonal projection from R2n minus 1 to Rn minus 1. So the projection can be written by A, B maps to A plus B times T. And if you work out the algebra, you will see that the PT defined on the previous slides gives us exactly the correspondence. That is, this orthogonal projection PT of E equals to the union of lines in Rn intersect with a hyperplane of height T. So the three blue points is the same as the three blue points here. And indeed, one can check that lambda is this collection of those n-1 dimensional subspaces in R2n-1, and those collection lambda lacks curvature, and there are some obstructions. That is, for example, when E is contained in some two-plane W, for example, E is, let's say, alpha 0, beta 0, where alpha and beta, they are like, say, in 0, 1. So this means n equals to 3, and E is in R2 times n-1, which is R4. Then we know that for any T, PT of E is just R cross product with this 0. So you call that PT of E is alpha 0 plus beta 0 times T. So only the first coordinate is non-zero, and the second coordinate is always 0. That is why PT of E always has dimension 1, but E has dimension 2. So this is the picture on the parameter space. In R3, this means that the lines parameterized by E is concentrated in a plane. And this obstruction only exists when n is greater or equal than 3. And this is precisely why the chi-ket set conjecture becomes difficult when the dimension is greater or equal than 3, because there is this obstruction. So the chi-ket assumption says that, since there is obstruction, we cannot hope to have a good projection estimate for an arbitrary set of E. So we need to have some assumption. The chi-ket assumption just says that the projection to the second half of the coordinates, to the bth coordinates, is 4, is the unit cube. And then the Kakeya set conjecture can be reformulated as follows. So for any E satisfying the Kakeya assumption, and for almost every T, the Hausdorff dimension of the orthogonal projection image PT of E, where PT is defined on the top, is n-1. So by Fubini, if you can prove this this version, then you could prove the usual version of the Kakeya set conjecture. So this is also indeed what Josh Zal and I proved. We show that in dimension n equals to 3, which means that if E is a subset of R4, and if it's away from any obstruction, so more precisely, it means that if it satisfies the corresponding Wolf axioms, then for almost every T, the Hausdorff dimension of the orthogonal projection image equals to the minimum of the Hausdorff dimension of E and 2. So our theorem can be reformulated in this way, and it is more general than the Kakeya set conjecture in R3. Indeed, it implies the Kakeya set conjecture. So previously, we talked about a viewpoint of the Kakeya set conjecture in terms of a projection problem. So for the Kakeya set conjecture, we take union of lines. But now, what happens if we don't take union of lines, but instead for each line we take, let's say, a small subset, an S-dimensional subset of the lines? So this is the Furstenberg set conjecture in R2. So this is a more general version. Let's say, since previously we defined a set of lines parameterized by E, so this is L, A, B, and E. We say that the Hausdorff dimension of a set of lines, we define it as the Hausdorff dimension of the set of its parameters. So recall that L, A, B is just A, the line connecting A, 0 and B, 1. Then the Furstenberg set conjecture is as follows. So suppose S is any positive numbers smaller or equal than 1, and T is strictly greater than 0 and smaller or equal than 2. Suppose L is a T-dimensional set of lines, and for any line in L, we have an S-dimensional subset of the line. Then the ST Furstenberg set is just the union of those S-dimensional subset of lines for line in a T-dimensional set. So F is those union of subset of lines. Then the Hausdorff dimension of the ST Furstenberg set is greater or equal than the minimum of S plus T, S plus 1, and 3S plus T over 2. So this Furstenberg set conjecture implies the previous Oblins conjecture for orthogonal projection in R2, also, which is the sharp version of Bourgain's projection problem. And the proof of this conjecture, the sticky case, important special case, was proved by Thomas Opponen and Pablo Schmerkin, and very soon after, the general case was proved by Kevin Ren and myself using the sticky case as a black box. So this Furstenberg set conjecture in R2 it has several applications. One is that this general scheme first proved the sticky case and then the general case. Also, we also use it in the proof of the Kakeya set conjecture in R3. And this also has application to the restriction conjecture in R3. So this is joint work with Shukun Wu. We showed that for any p greater than 3 plus 1/7, this restriction estimate holds. So this restriction estimate, previously we said how restriction conjecture implies the Kakat set conjecture. So this implication also holds if we have some partial result. So here we have a partial result of the restriction estimates, and then this implies the Wolf's estimate on the Kakat set in R3, saying that any Kakat set in R3 has Hausdorff dimension greater or equal than 5 halves. And this estimate is important because Wolf's method is sharp for sets in C3. Finally, let's just go back to the wave packet decomposition, and I want to try to convince you why we should think about the Furstenberg set estimate instead of the Kakat set for restriction conjecture. So previously, we studied this wave packet decomposition, and then to understand those F, we need to understand how wave packets overlap. But for the Kakat set, we take the union of the entire line, or in other words, we take the union of entire tube. But when we want to estimate sum over the wave packets, there is no guarantee that each point on the tube plays the same role. For example, this part of the tube, there are no other tubes passing through it, so it should carry less weight as the middle part of the tube, where a lot of other tubes point through it. So that is why instead of considering a union of tubes, we should consider a union of some points of the tubes. And this is precisely the object of study for the Furstenberg set conjecture. So I will stop here. Thank you very much.
Well, thank you for this beautiful talk. So any questions from the audience? Okay, everybody understand the talk? Thank you.
Now we have 10 minutes break. Thank you.
请到跟着公主到不好意思，我们来卸一下麦克风啊。不好意思，我们先要卸一下麦克风，我们先卸一下麦克风。 我在想怎么抓它。我去厕所门口蹲它哟。有瓦佩斯先生出来了吗？邓玉还没找。
邓玉已经好
来了是吧？他带好了。
盯上了，现在就
好的。我去找。我知道，他穿了件白衬衫。我又开始脸盲了，
找不到是谁。
我看一眼小抄，是他。
这个应该都得出西藏南北。
是个地方。我不该是多。我挂一个女生公主表。
say something about the speaker?
Yeah, say something
okay.
about speaker and when he finish his report.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
我来跟他说一下吧。
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
They are coming back now. 等他们再回来一下吧，不然一边说话一边走路，其实我觉得有点不礼貌。刚刚邱先生就该看大家在往里面走，外面有人在叫他们回来吗？我听到铃声了。听到铃声了是吧？
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
，Where is the speaker?
You go first.
Okay, but he is ready. Where is he? He is ready.
Yeah, he's ready.
Okay. Okay. Good afternoon. I'm happy to introduce our next speaker, Professor Yu Deng from University of Chicago. He has numerous honors, 4 or 5 of them just this year, but I want to start with his gold medal in the IMO in 2006 and Putnam Fellow in 2010, because people often say, well, you know, mathematical competitions are not important for research, but in some fields, somehow the spirit of competition can carry you to amazing research advances. I should say that as a probabilist, you know, we studied Varadhan's method of getting to PDE via microscopic interactions, and the general principle, well, this is impossible for hard sphere and Boltzmann equation, but that's exactly what Professor Deng has succeeded in. So again, he received the gold medal here today. He's an ICM speaker in the upcoming ICM later this year. Let's all welcome Professor Yu Deng.
Okay, thanks very much for the kind introduction. So today I'm going to talk about my recent work on this general topic of Hilbert-6 problem, and in particular the derivation of kinetic equations in both particle and wave settings. So the wave part is a joint work with Zhao Hanny from University of Michigan. The particle part is a joint work with Zhao Hanny and Ma Xiao, who is also from University of Michigan. So how do I go forward? Is there anything I can click? This. It's here, sorry. Okay. So the starting point, well, there was this so-called Hilbert-6 problem, like with a big title of mathematical treatment of axioms of physics, like as in the Hilbert's original list in the 1900s, and later on, he also wrote an article in the Bulletin of AMS in 1901, I think. So of course, this is, this title is extremely broad title and could include essentially anything in mathematical physics, and certainly we are not talking about this problem in this generality. But on the other hand, what Hilbert actually had in mind, when he proposed this problem, was a particular, question concerning the kinetic theory, which was about 20, 30 years old at that time. So he was mentioning, in his article, that about the problem of developing mathematical limiting process, and limiting process is a process referred to in Boltzmann's kinetic theory, which lead from an atomistic view to the laws of motion of continuum. So basically, we start from the microscopic point of view of interacting particles, and we want to end up with this continuum description, which let's say the fluid equations. Okay. So this is the kind of the broad topic we'll be talking about, and then there are basically this process can be divided into two steps, at least with one kind of picture that we currently understand today. That we first take this kinetic limit. So kinetic limit goes from the microscopic particle systems to this mesoscopic kinetic equation, and in this case, this will be the Boltzmann equation. Okay, so basically we start from this huge number of interacting particles, and then by considering the distribution of these particles in space and the velocity space, we reduce this almost infinite degree of freedom system to a system of finite degree of freedom, which is this Boltzmann equation. Okay, so this is the first step. Well, the second step is by taking this hydrodynamic limit, namely where we take this collision rate, we'll see in a few slides, and we take this collision rate and let it go to infinity, and then we're going to see that this density function described by the Boltzmann equation, this density function will be relaxing to a local equilibrium, in velocity, which are Gaussian functions in velocity, and then these corresponding parameters of Gaussian, the mean, the variance, and these days they are exactly the field satisfying the fluid equations. Okay, so this is this two-step process, and of course, as I said, so there are different understandings, but here we're taking this particular approach. And then in this talk, we'll be focused in the first part of this limit, because the second part, the hydrodynamic limit, has been kind of well understood with the works of many great mathematicians, including Cavendish, Damasi, Esposito, Velasquez, and Gauss, Ceremony, and a lot of others. So basically, we know kind of how this hydrodynamic limit works, and the question is how to derive the kinetic limit in a way that allows us to connect to this hydrodynamic limit. Okay, so this is a picture. We start from these particles. I don't know, the laser doesn't seem to work, but okay. So let's say these particles belong to a finite box. We can consider either a parodic box or kind of infinite space, but we restrict them by a decaying density function. It doesn't really matter. Let's say in a three-dimensional domain, and we have n particles, where n is going to infinity in the kinetic limit. So n is the degree of freedom. Okay, so we are taking this mathematically simplest picture, which is a half sphere picture, where we assume that these particles have diameter, epsilon, and they're half spheres in the sense that they interact only when they directly collide with each other. So this is the picture like on the top, on the bottom right. We have two particles with a velocity v pre and vi pre and vj pre, the pre-collision of velocities, and they touch each other and they collide and they go away by these post-collision of velocities. Okay, and there is a particular formula between these pre-collision and post-collision of velocities, which we'll see in the next slide. And finally, so there is this relation between the parameters n, the number of particles, and the size epsilon, which is the size of particles. And here we're taking the so-called Boltzmann-Grad scaling, where in 3 dimensions that is n times epsilon squared equals alpha. So let me explain what this means. So basically what happens here is that if you have a unit box, and you have n particles in total, then if you take any particle of size epsilon, and then let's say it goes through like a unit distance, so that's a unit distance, 1. Okay, then the volume of this region that it covers is volume like epsilon squared. Okay, in 3-dimensional that is epsilon squared. And if you have n particles in the unit volume, then in the epsilon squared particles, epsilon squared volume, you're going to have n epsilon squared particles, which is alpha. So this alpha basically means the average number of collisions that a single particle will see or have when it travels distance 1. Okay, so alpha equals average number of collisions for a particle, let's say at this distance 1, when it travels distance 1. Okay, so we're assuming this alpha is essentially a constant, or kind of very slowly varying parameter. So that's what we call the Boltzmann-Grad scaling. By the way, this is a kind of low density setup, because if you n, so n equals alpha times epsilon minus 2, which is epsilon minus 2. Well, in the dense case, where you try to fix these epsilon balls in the unit volume would get you like epsilon minus 3 places, but you only fill them by epsilon minus 2 balls, which is a kind of low density setting. So there are results in the high density setting, epsilon minus 3, but these are kind of only in the stochastic setting, which I'll maybe talk about in a little bit. But okay, so this is setup. We are assuming the so-called Boltzmann-Grad scaling limit. Okay, so this is the formula. This is pretty elementary. Like the way of elastic collision works is an elementary formula. Like if you have this, epsilon omega being the vector connecting the two centers, then basically the velocities orthogonal to omega will be preserved, while the velocities in the direction omega will be exchanged, and that is this formula here, like in the 2 middle lines. And this you can define it apart from suitable technical issues. It is time reversible and volume preserving dynamical system. Okay, so now we start with this system, and as I said, we'll take the statistical point of view. That is, to consider the distribution of all these particles in both the physical space and the velocity space. Okay, so that is we consider this so-called S particle density function. So this S particle density function, so first of all, when S equals 1, you have one particle density function, which means one particle F1, which means the density function at time t, such that how many particles have this velocity, position x, and have this velocity v. Okay, so the probability density describing distribution of particles. And then if you have Fs, then Fs, so this is the probability density of the first particle having position x1 and velocity v1, the second particle having position x2 and velocity v2, and S particle having position xs and velocity vs. Okay, so these density functions, you can see that under this evolution by the Hart-Sphere system, you can write down the equation or the system equation satisfied by this density function using Liouville's equation. Okay, so you see that these density functions, they evolve kind of according to Liouville's equation, which is derived from this Hart-Sphere system. Okay, we also have initial data. At initial time t equals 0, we make this assumption that this S power density function is factorized. Okay, so at t equals 0, we're going to see this Fs equals F1 tensorized. Okay? And now we have this initial data, we have this evolution. Then the question is, how do we describe the time evolution of these density functions? Let's say in the limit, in this kinetic limit, where n goes to infinity and epsilon goes 0 according to the Boltzmann graph. Okay, so you see that this initial factorization, this tensor product representation, on the physical level, it means that the states, the position and velocity of different particles are independent. Okay, so this means the probability of the x1 v1 and x1 vs is a tensor product, means that the state, the position of first particle, the second particle, and s particle, they are all independent of each other. Okay, and this is exactly corresponding to the molecular chaos assumption in kinetic theory, that the behavior of different particles are independent of each other. And then the point here, the physical intuitive point, is that this independence should somehow be preserved, like in the kinetic limit, like even with when you have time evolutions. Okay, so this is this famous kind of a claim, kind of physical belief of propagation of chaos, which of course is the main mathematical challenge, like in this whole problem. Okay, so now let's put that aside, for now. Assume we have propagation of chaos. Okay, then at time t positive, then still the whole statistics of these S particle densities is still given by the tensor product of the 1 particle densities. And then if you assume this, then you can formally write down the evolution equation that this 1 particle density function should be satisfying, which is this Boltzmann equation. So let me show it here. So this is on the left-hand side, we have a linear transport, which means that if there is no collision, then everything goes linearly, then the density function just transported by this linear transport. And then the right-hand side, measures the effect of collisions. So alpha is precisely this alpha, which is this collision rate. And then, this Q is a collision operator. In the hard sphere case, it's given by this simple expression. So we write it in the unusual way with 2 delta function, which is the same as the wave kinetic equation we'll see in later parts. But really, what happens here is that you are looking at the velocity v. Okay, you're looking at the particle velocity v. So how do you get new particles of velocity v? You get them by, maybe let's write here. So you get the particle of velocity v by colliding 2 particles. So this is v1, this is v3, and you get v and v2. Okay, and these 2 delta functions exactly correspond to the conservation of momentum and conservation of energy. Okay, and this corresponds to this positive term, like on the right side, which is a gain term. In the same way, how do you lose a particle of velocity v? You lose it by colliding it with something else. Okay, and then you get this negative term, and these are exactly factorized f1, f3, and ff2 precisely because you're assuming different particles are independent. So the 2 particle density function is factorized into 1 particle density. Okay, so this is the precise kind of description of the system. We start from this particle system, and we describe this evolution of density function. We expect if we have propagation of chaos, then this density function is going to satisfy this Boltzmann equation. And of course, the question is how do you justify everything here mathematically. So let me go through a little bit of the timeline. So starting from the kinetic theory of Boltzmann in the 1870s, and everything here was obtained kind of under this propagation of chaos assumption, which was really just a physical assumption that was made in this work. While then the work of Grad, kind of in the 1940s, was the first precise mathematical formulation of the kinetic limit, and in particular was the one who proposed this first proposed this Boltzmann Grad scaling. And there are these works, in the 1950s, between 1950s and 1970s, were introduced the BGKY hierarchy into this problem, which was one of the dominant strategies, for many years. And also let me mention these works of Keck, the known by the Keck's model, and also work of Morey, kind of again in 1950, where they studied kind of stochastic models where each collision brings you randomness, and in this case, the problem is actually much easier to derive. Okay, so back to the original setting, like in the Boltzmann-Grad limit, and in the deterministic dynamical systems, the first derivation was done by Lanford, and also in the same time by King in 1975, where they were able to rigorously derive the Boltzmann equation, let's say with the collision rate alpha equals 1, for sufficiently small time. Okay, so for sufficiently, a small time, basically at which time you are not, you're still having kind of very few collisions on average. Okay, and after that, there has been a lot of subsequent works. Let me mention the work of Illner and Poverenti in 1986, where they obtained the long time extension, but in the case where alpha is much less than 1. Again, that's a case where I have a very few expected number of collisions. And in the last 10 years, there's this group, Gallagher, Ceremony, Texier, and both, Gallagher, Ceremony, Simonella, where they complete a lot of nice works, regarding, for example, this firstly, improve the work of Lanford, and secondly, obtain this linearized Boltzmann model and deriving the equation fluctuations and many more. So I will not have time to go through everything of every one of these work. They are great results. But let me just mention that all these results are restricted to either the short time setting or kind of the otherwise perturbative setting. So basically, essentially, you are restricting yourself to the case where each particle is only going to have a few, not just a few, but like on average, like 1 over 1,000 collisions. On the other hand, like if you really need to connect your kinetic limit to the hydrodynamic limit, so I didn't say that in hydrodynamic limit is where you take this alpha to go to infinity. Okay, so you are seeing like many collisions, the collision rate going to infinity in order to see this relaxation to equilibrium. So in order to connect this limit, you really need to justify this kinetic limit in a setting where alpha, can be arbitrarily large. And that's the thing we are trying to do, like in our research. The question is, can we derive Boltzmann equation from Hasse models for arbitrarily large time, at least for arbitrarily large collision rate alpha, as long as the solution to the Boltzmann equation exists? Okay, so this is the first half of the picture. These derivation of kinetic equations in the particle setting. And then we turn to the kind of the dual setting, which is a wave setting. Okay, so at the time of Hilbert's lecture, of course, there was still not much known about quantum physics, but in 20 years or 30 years, people was already kind of starting to understand a lot about this dual picture, of quantum physics, especially this wave-particle duality. Okay, and then there has been, of course, dual theory, kind of to the theory of particles, namely the theory of waves. And if you want to study the statistical kind of physics of waves, that exactly leads to the subject of wave kinetic theory, or we also call the wave turbulence. Okay. So in here, we'll see, like in the next few slides, how general what is the setup of these problems. But really, the role of Boltzmann equation here is replaced by the wave kinetic equation. So this starts with work of Nordheim, Peirce, and these people in 1920s, 30s, and there has been fundamental contributions by Hasselmann, like who worked on the wave kinetic theory for water waves, and by Zakharov, who worked on the general setup and also introduced this Kolmogorov-Zakharov spectrum, which brings the subject the name of wave turbulence. Okay, so this theory, I want to say that it has been applied to kind of actual scientific, scientific predictions. So left-hand side is a picture taken from the Simon's collaboration on wave turbulence, which is a picture where we use a wave kinetic equation to predict the movement of ocean surfaces, and right-hand side is a picture on the application wave turbulence to the plasma theory. So in general, there are kind of lots of applications because this picture describes the interaction, the statistical interaction of waves, and waves, occur in many different scientific settings. Okay, so the precise setup. So here, I'm describing this setup kind of in parallel with corresponding particle theory we just heard like in a few minutes ago. So here the particles are replaced by waves, and there can be either homogeneous or inhomogeneous settings. In the homogeneous settings, the waves are just Fourier modes. Okay, so they are homogeneous everywhere in space. In the inhomogeneous setting, their wave packets, they vary kind of in intensity in different space and different frequencies. But in any case, these things, they live in a large box of size L. Okay, so let me draw this picture here. A large box of size L. Okay, and then if you consider the Fourier modes, let's say, the Fourier modes is like a mesh of distance 1 over L. So this is 1 over L, okay? And let's say we are considering a kind of a medium frequency theory. So let's say we draw a ball of, okay, so of frequency size 1. And if you think of the frequencies are these Fourier modes, and the number of Fourier modes is, L to the 3, like in 3 dimensions. Okay? So basically, we are considering these interactions. So considering these interactions of waves, these waves live in this large box of size L, and the number of interacting waves is given by L to 3. And of course, L is going to infinity. So this is our kinetic limit. So degree of freedom is L to 3. And what about collisions? Collisions are replaced by nonlinear interactions, modeled by nonlinear dispersive equations of strength of nonlinearity being alpha. Okay, so we'll see an example, which is a cubic Schrodinger equation. Let me say that this is not the only nonlinear dispersive equation, but of course it's a canonical one in some sense. And of course you can write down the system with any different equation, for example, the water wave equation, and you can always write down corresponding wave kinetic theory kind of by the same formula calculation we are doing like right now. Okay, so we are just taking one example with a Schrodinger equation. Okay, so here this parameter alpha represents the strength of interactions, and in the limit is alpha going to 0. So that's corresponding to a weak nonlinearity limit or kind of weak coupling limit. Okay, so we have this picture, like this Schrodinger equation in this large box with alpha going to 0. And as in a simpler kind of setup, we'll be dealing with homogeneous cases, although we believe the inhomogeneous cases should work the same way. And in the homogeneous case, there is actually some flexibility in the scaling relation between the parameters alpha and L. So assume this alpha and L scales like alpha equals L to minus gamma for some gamma between 0 and 1. Okay, so once we fix this scaling, then we're going to take the limit where L goes to infinity and alpha goes to 0, and we're going to see discuss the statistical behavior of the solution to this equation, of course, in this limit. Okay, so this is the initial data we are taking. So the initial data, since we are in a homogeneous setting, our interacting waves are just Fourier modes. And again, like initially at time 0, we assume these Fourier modes are independent. So that's the initial kind of molecular chaos assumption. So we have this U hat k being a square root of this function called the profile. It's a fixed like a non-negative Schwartz function times eta k, which are IID Gaussians. Okay, okay. And then we talk about the statistical behavior, statistical quantities of the solutions. And here, like remember in the particle setting, we're having this 1 particle density and S particle densities. And in the wave setting, we're having the 2-point correlations and the 2 S-point correlations. So you have this 1 particle corresponding. You have these 2, let's say, you had TK squared, these 2-point correlations, and the S particle, it corresponds to, let's say, the expected value of the S particle, 2 S-point correlations. Okay, so this is the statistical kind of information we are looking at. And then we have, as I said, we expect to have this propagation chaos. So let me mention one thing, that there is this notion of kinetic time, which is given by alpha minus 2. And this exactly corresponds to the time, where the first nonlinear interaction happens, which corresponds to this parameter, this parameter where the expected number of collisions. And here it's like you can think of the expected time where the first collision happens. Okay. So we expect, as in the past example, we expect this propagation chaos, independent Fourier modes should be preserved. And if you assume this, then these random variables, you take this, you take this kinetic time, you rescale your time by this, so you set t equals tau times t kinetic, so we're considering tau being a constant. And then for any constant tau and different Fourier modes k1 to kr, then these Fourier modes will be independent or asymptotic independent in this Canyon limit. So this is the propagation chaos. Okay, so if we assume this, again, like this is highly non-trivial, but if we assume this, then we are going to have these general kind of 2R point correlations. As I said, this is going to be factorized into the 2-point correlations. Okay, so if you assume independence, and then we're having is almost equal to the product J, you had T Kj square. Okay, so these are 2-point correlations. So by the way, let me also mention that these are not the only like 2s order correlations. So they are actually also like more general, let's say, K1 plus minus (2s). Okay, so you have in general, these kind of general correlations, but really the leading term of these general correlations will be 0. Okay, so it's a product J. You had T Kj, let's say 2J minus 1, so square, if you have these so-called pairings. And all the others are 0, almost equal to otherwise. So in some sense, that these are really the only kind of correlation you should look at. And once you assume propagation chaos, then they will be factorized into this. Okay, so this is propagation chaos. Assume you have propagation chaos, then these general 2R point correlation can be factorized into these 2-point correlations, and the key quantity is now these 2-point correlations, and they are going to satisfy an equation which looks exactly similar to the Boltzmann equation, which is the wave gain equation. Right? If you look at this, you're having this. On the left-hand side, you have d tau because you are in the homogeneous setting, so you don't have the transport. Like there will be a transport if you are in the inhomogeneous setting. On the right-hand side, you see you have the same delta function, like exactly the same delta function, except now the velocity is going to be replaced by the frequencies. And the only difference between this collision operator and the Boltzmann collision operator is that you're having a cubic term here, like f1 f3 times f plus f2 instead of f1 f3. And this is simply because you're starting with the cubic nonlinear Schrödinger equation. But otherwise, this is exactly the same as what you see in Boltzmann equation. Okay. So this is the kind of the basic description of the theory. You start from this Schrödinger equation representing the interaction of many many random waves, and you take the statistical behavior of the solution, and you end up having this 2-point correlation satisfying the wave gain equation. Okay, so a few remarks as I'm explaining here, like we're in a homogeneous setting, so there is no transport. Otherwise, you're having a transport term which makes you kind of much more formally resembling the Boltzmann equation. And second, the collision operator is cubic, but with the same Domino integration. And finally, there is quantum Boltzmann equation, which is written down in the 1920s, whose derivation is still completely open today. But this quantum Boltzmann equation is really the nonlinearity for the quantum Boltzmann equation. The collision integral is really just a linear combination of the quadratic one from the Boltzmann equation and the cubic one from the Wave-King equation. Okay. So about this line of rigorous mathematical works, so the thing started with Spohn, work of Spohn in 1977, where in the earlier times you have been looking at, have been focusing on the the linear problem, basically considering the linear Schrödinger equation with a random potential. And there was a sequence of works, and then by Spohn, and then by Erdős and Yau in 2000, and finally by Erdős, Samhoven, and Yau in 2008, where they were really able to extend this whole theory to the kinetic time and even beyond the kinetic time, to the kinetic time to the sum power 1 plus epsilon. And this is really specific to the linear model. But really, they're able to get these really kind of like amazing results, going beyond the kinetic time. And then starting with the nonlinear problem. So the first one was by Lucaroni and Spohn in 2011, where I consider equilibrium kind of, which is the Gibbs measure, of the system. And they're considering the correlation between time 0 and time t, for a large time t, and they're able to derive, linearize the kinetic equation, for these correlations. Okay, and then people started working on the, non-equilibrium settings, which was, first work was due to Buckmaster, Germain, Hani and Chattah in 2019, where they considered the nonlinear problem, of equilibrium, but with a much smaller time scale than what you should get at kinetic time. You have kinetic time to the kind of 0.3 or something. Fine. And subsequently, in the independent works of myself with Hani and independent work of Collor with Germain, we're able to extend this result to kinetic time to the 0.99, which is arbitrarily close 1. But still, if you divide by the kinetic time, it's still kind of zero limit, like a vanishing limit, like relative to kinetic time. And kind of the first real thing in this, real thing that reaches the kinetic time was by myself and Hani, kind of in a sequence of works in 2021, 2023, where we're able to first, get to this kinetic time multiplied by constant time tau. So tau is an absolute constant that doesn't go to 0 in the kinetic limit. So really, we are really seeing this. So the question is, okay, so starting from time 0, there is nothing happening at time 0. We're going to, let's say, first of all, at time t kinetic to the 1/2 minus. So there's something happening here, which is still vanishing in the limit, but you're starting to see a little bit of nonlinearity, and you get to t kinetic 0.99. Okay, and finally, you're going to get 0.01 times t kinetic, where you're going to really see the effect of a nonlinearity, kind of, in the average setting. Okay, so this was what we did kind of in this sequence work 2021 and 2023. Now I see this. Okay, but okay, so that was kind of the situation, at the time before these main results, before we get to these main results. And when the key question is how to get to longer times, instead of 0.01, can you get to 100 times the kinetic? And of course, for Boltzmann, the same thing. Can you get to this time kind of 100 instead of 0.01 collisions? Okay. So this is the time to introduce our main results. So the first one was joint work with Hani in 2023. So we're able to justify, suppose a solution to the wave equation exists in any given time interval. So here the tau star can be arbitrarily large, and the solution, of course, can also be arbitrarily large. Then in any case, uniformly on this whole interval, we're going to have these 2-point correlations equals the solution to the wave-King equation plus the remainder that vanishes in the kinetic limit, and everything is uniform as long as your solution remains smooth. Okay, so this is the first thing that we are able to, in the wave-King sense, we're able to justify everything, the whole theory up to this time, provided your solution exists up to this time. Okay, and this was a first work on the Wave-King equation. And then subsequently, in the next year, we're able to extend this to the Boltzmann equation again. So here's the thing. So suppose the solution to the Boltzmann equation exists again on a given time interval, which can be arbitrarily large, and solution can be arbitrarily large. Everything can be arbitrarily large. Then we have this. So you see, this one is a combination of proper Canonical chaos. So the S-power density is a factorized thing, and this 1-power density is given by the solution to the Wave-King equation. In this case, the Boltzmann equation, plus remainder again, like explicitly going to 0, like with the power law, in the kinetic limit. Okay, so of course the same thing can also be written down in the Wave-King theory, but just that we didn't have enough room to write it down. But you also have proper Canonical chaos and everything like you would expect from physical intuitions. Okay, so this was the second result we were able to prove, and since this allows the time to be arbitrarily large, this allows us to connect this kinetic limit with hydrodynamic limit so that in the end we could completing kind of both steps in Hilbert's original program, like in the Boltzmann grad limit. So let's just show an example of the theorem that we get. Start from the Hart-Sphere system. Like in torus, like it has to be torus for some reason I'll not be explaining in detail. We start from this initial data, which is this Gaussian kind of local equilibrium setup. Then, as long as we take this iterated limit, you first take the kinetic limit n goes to infinity, and you take a hydrodynamic limit alpha goes to infinity. Then you see that at any later time, this 1-power density will still be given, by this local equilibrium Maxwellian form, but with its parameters rho and t and u, they are exactly satisfying the fluid equation. In this case, it's a compressible Euler equation. Okay, so then you have been able to go from the Hart-Sphere system via the Boltzmann equation and eventually go to these compressible Euler equations. And in the same way, you can also derive the Navier-Stokes equation, provided you consider global equilibrium and perturb around it, and you look at kind of longer time scales to see dissipation. Okay, so this is of course just a part of the theorem, and essentially like any kind of fluid limit that can be derived from Boltzmann equations can also be derived from the Hart-Sphere system, by our theorem. Okay, some remarks. So maybe let me just explain the first remark. As I said, these tau star can be allowed to be arbitrarily large. So as I said, it can be allowed to be arbitrarily large, but really, like our theorem allows you to let it go to infinity in a kind of a little bit, like go to infinity a little bit in the sense that it can grow like a log of the main parameter you are having. So it's a very important question whether you can prove it. You can prove it to a power of log or even a power, but that's kind of far away. Like for now, we can only get a log. But it's a very interesting question whether you can prove it. Okay, so this is a brief discussion of the problem we are looking at and our main theorems. And so we still have some time, so let me explain a little bit the ideas involving the proof, and maybe in the end a little bit of open questions. Okay, so what is the idea of proof? So the first question we should answer is like why, like all the previous works, are restricted to short times? Okay, what's special about short time? The thing is the following. So if you have a short time, what you do is that you're going to perform an expansion. Let's say we either take the collision particle setting, or we take the nonlinear Schrödinger equation. Doesn't matter. Let's say we take the colliding particle setting. Okay, so how do you express the density function at time t? Okay, so you are going to classify this density function into by the profile of collision. So let's say we have no collision. Okay, we have no collision. Then the density of this particle is simply transport because this particle just goes linearly. Okay, and then you are having, for example, one collision. Okay, then what you have is you are looking at density of this particle, F1. The density of this particle is going to be given by an integral because you choose another particle, another particle that collides with it, and you integrate in the velocity of that particles such that you have this collision, and then you get the density function of this particle. Okay, because when you have one collision, then the velocity is going to be determined by the velocities of this particle and that particle. Okay, so this is the one collisional case. And you have two collisional cases, like even more complicated. Let's say, let me draw it like this, and then you have another collision. Okay, this is two collisional cases. And again, this one particle density is going to be integral given by the velocity of this guy, the velocity of this guy, and the velocity of this guy. Okay, so it's an even more complicated integral. What's the point here? So this, the size of this is OT to 0. The size of this, you have one integral, the time between 0 and t. So this is O of t to 1, and this is O of t to 2, and so on. So the thing is that you're going to take all these diagrams, and you're going to match these diagrams to the expansion to the Boltzmann equation, which I'm not writing down, but you're going to match it to the the linear transport. Okay, so the L linear transport F, and this is, let's say, L0 with a collision operator. Let's say L0F, L0F, so second iteration of Boltzmann, and this is going to be L0 Q of L0 Q of L0F, 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 something like this. But in any case, you see this is a third iteration of Boltzmann and so on. Of course, there are also kind of leading terms look like this. There are also subleading terms that go to 0 and so on. But in the end, you are going to match this with this term by term, and you show that the sum of these converges to the sum of this. The point is that in order for this sum to converge at all, you need t to be small because it's a power series. So this power series need t small. So this is a fundamental reason like why in all the previous works we have been assuming the smallness of time. Okay, so now how do we get to longer time? The first first question is now we cannot like do this iteration for the whole time interval now that t is large. So what do we do? The strategy, kind of the very intuitive strategy, is to divide you have t 0. You divide your long time interval into a large number of short time intervals. So you have this 0, this is tau, this is 2 tau, this is 3 tau, and so on. So this is L times tau, which is equals t. Well, L is very large. Okay? You're dividing your long time interval into short time intervals such that you try to say that you propagate something from 0 to tau, and from tau to 2 tau, and from 2 tau to 3 tau, and you're all the way going down to this time, and you try to kind of do an induction argument here. Okay, so this is what you call the time layering here, like divide a long time interval into short times. Okay, so now you're seeing one question. Okay, so of course, when you work on each individual time interval, you'll regain convergence, fine. But the problem is that this argument here relies on the fact at time 0 you have independence, or kind of molecular chaos. And here at time 0 you also have this independence. But at time tau you no longer have independence because you're having collisions. Of course, like you are having independence in an asymptotic way, but really it's this remainder term really matters a lot. So you need to find a way to describe it. So what do we know here? Okay, and of course, like once we know what happens at time tau, we need to know what happens at time 2 tau. What do we know here? And so on. So basically, we need some information describing the ensemble at time 0 you have independence. At time tau, we need some description. At time 2 tau, we need some further description. At 3 tau, so on. We need a sequence of descriptions of these ensembles that kind of allows us to propagate in time. Okay, So one way to describe, the ensemble of many different random variables that are not necessarily independent. If they're independent, then you are fine. If they're not necessarily independent, you are going to describe them by these cumulants, which is this. Okay, so the joint density, as part of density, is going to be a sum of these products. So the product terms, so H is a subset of particles. So the product means that those particles not in H are independent, and those particles in H will not be independent. Okay, you separate those independent particles and those dependent particles. Okay, and then we get this formula with these cumulants. So basically, the cumulant describes, how these particles are dependent on each other, and really, this is the information we need, to describe the ensemble, at each times. So formally, kind of. In a schematic way, we're going to say that if the cumulants at time L tau satisfies something, So let's say something. Then, something with subscript L, then the cumulant, because if we know the cumulants at time L tau satisfies something, that means we have some description of the cumulants, of course, and the general ensemble, of all these particles. Then the cumulants at time L plus 1 tau will satisfy same condition, L plus 1. Okay, so this is our scheme. And the scheme is that we are going to determine what condition we have here. Okay, and then here's the thing. So this is the first page of the kind of a summary of the proof. Then what happens here, is that you are going to write your cumulants as a sum of expressions in terms of the interaction history diagrams. Okay, so let me say the answer. So this condition means the cumulants at L tau is a sum over diagrams between time 0 and L tau, let's call it M, and of this I of M, which is this integral defined by M. Okay, so you see you're propagating this condition. Like this condition is a exact expression for these cumulants, which means that if we have this exact expression for these cumulants at time L tau, then we have this new updated exact expression of these cumulants at L plus 1 tau, where we replace this L by L plus 1. You think of it this way, at time 0, there is no cumulant. Everything is independent. Okay, at time 1, you are seeing some cumulants. The cumulants are dependence of particles, which come from interactions of these particles between time 0 and tau. Okay, so at time tau, you're starting to see some cumulants, which is described by this so-called one-layer diagram, because M is 0 to L, it has L layers. So time tau, you're going to have cumulants. This is one layer. Let me use a different color. So this is one layer diagram. And at this time, you're having two-layer diagram. At 3 tau, you're having 3 layers, and so on. Okay, these things kind of build up, more and more complicated. And this is the picture. Okay, you see the left-hand side is a particle picture, which we have been describing. Right-hand side is a wave picture, which I'll explain a little bit later. You see on the left-hand side of the particle, we just have 2 layers, from 0 to tau and tau to tau. Okay, so the the circle means collisions, okay? And the lines means particle trajectories. And in different colors means different particles. So see there is a blue, for example, there is a blue particle. It collides with a red, fine. And blue goes this way, red goes this way. And then blue collides with green in the second layer, fine. And then red collides with a pink in the first layer, and pink collides with blue again in the second layer, and so on. Okay, so this diagram is a diagram describing all the relevant collisions, divided into different layers. So on each layer, you're going to have some collisions, and these particles they cross, between different layers. Okay, so this is M. This is diagram M, and then it has L layers. In this case, in this case, L equals 2. And then you have this integral. Okay, so this integral IM, I'm writing down the the formula here. This IM is an integral with the input function, which are these solution to Boltzmann equation, and this delta, which is a Dirac function, representing the collision formula. For example, if you have a collision, then you have V1, V2, V3, V4. They're going to satisfy some equations which are given by these delta functions. Okay, these delta functions. Okay, and then you collect all these among the whole diagram, and then you're going to get this integral. And on the right hand side, we have the wave system, which is the same thing. Essentially, here each point represents a cubic interaction. Remember, you have a cubic Schrodinger equation, so you have a cubic interaction. And then these leaves are the input function. Remember, you have Gaussians, so you have these input Gaussian. But when you take correlation between Gaussians by weak formula, you're going to have the pairings between these Gaussians. And here the red pairs with red, pink pairs with pink, blue pairs with blue, and so on. Okay, so and here this is diagram. Okay, so you see in any case the cumulance is a sum over all the diagrams. Diagrams is on the left in the wave case, like the right in the particle. So in the left in the particle case and right in the wave case. And then you have this IM, the integral, which here you are having this input functions, solution to wave equation. And here the only difference here you have the oscillator integral in time. But once you integrate out, you again get delta function, which are exactly the same delta function you see on the left. So see, these pictures are exactly in parallel, like in the wave and the particle pictures. Okay, so this is the idea. We divide the times. We try to propagate these n-sets. These n-sets given by cumulants. The cumulants are given by this sum over, of these huge integrals over huge diagrams. Then what is left? What is left is to control this diagram, because you don't want this sum to be infinity. You don't want this sum to be divergent. You want it to converge. Okay? So in order to show them to prove they are converged, you need to control the integral. You need to control the number of diagrams. Okay, so this is the last slide of proof that there are two I cannot explain this in much detail, but I can only say that how to control these diagrams. So there are two ways to do two steps to do this. So one, remember that you're going to control this IM. So you control, let's say control IM for each M, individual M. And then we control the number of M. Okay, so these are the two things to do. So basically, the first thing, I control IM, is an analytic analytic component where we control a big integral. And second thing, you control number of M is a combinatorial, component where you control, this number of diagrams. And actually, in the end, you need to do some operation to these diagrams to define a particular parameter, and you control the number of diagrams according to that parameter. But in any case, there is an analytic component, and there is a combinatorial component. So it turns out that very interesting, the analytical component in the Boltzmann case is trivial. Not trivial, but it's pretty easy. You just do integral, everything is positive. But in the wave case, you need a very delicate cancellations in order to estimate all these integrals. So the analytical component is much harder in the wave case. On the other hand, the combinatorial component is actually much easier in the wave case and much harder in the Boltzmann case, in the sense that you need to design a suitable cutting algorithm in order to to reduce your big diagram M into smaller diagrams. So let me show this picture. For example, here you have 4 points. What you can do is that you perform a cutting, let's say you cut Okay, cut, for example, along this line, and then you are cutting this into a two diagram. The first diagram with the 2 top points, and the second diagram with 2 bottom points. And by repeatedly doing this, you are going to divide your whole huge diagram into a large number of small diagrams, such that you have a good estimate for each individual small diagram. And the combinatorics, the algorithm will tell you, what is the number of each type of subdiagram, and you can put this together. You get a control of the whole diagram. And this is a kind of really the hardest part, like in the proof of the Boltzmann result, like with this cutting algorithm. Okay, so I think that's only thing I can say regarding proof. Maybe in the end, let me mention a few open problems, like in the direction of in the wave turbulence. Of course, there is this quantum Boltzmann equation, which is still completely open. And the question of the Zachar spectrum, where how you really see this Zachar spectrum first on the level of a wave-King equation, and then maybe on the level of the Schrödinger equation. And of course, there is formation of delta singularity due to Escobedo and Velasquez. How do you see that even in the Schrödinger setting? And finally, there are these question of quasi-linear equations and 1D turbulence. There seems to be a lot of anomaly, like so what I said, our theorem is in 3D and higher. Like in 2D, the theorem should in principle work, but in 1D, they will break down. And really what happens in the 1D, like in the wave-King equation, is something unclear. Finally, some questions about in the direction of Boltzmann equation. So there is a fluctuation result by Bodino, Gallagher, Ceremony, and Simonella, like can extend it to long time. And what happens if you go beyond the Boltzmann graph? I believe that's a very hard question. And currently there is no methods like unless you add randomness. And of course, what happens with singular solution, like a weak solution, like there is no uniqueness, and how can you take the limit? I mean, suppose you don't want to take a subsequence limit, like you want to take a real limit. This is a big question. And of course, like general potentials, short-range potential, we believe it can be done, and long-range potentials, it depends really on the decay rate. Like if you decay slower, the slowest will be the Coulomb interaction, which the Boltzmann doesn't really make sense, but you are going to get a Landau equation in a suitable case. But even that is, again, it's completely open, at least even for a short time. So you see, there's still a lot of things to do, and I think I'll stop here, like with these questions. Thank you.
Thank you for a marvelous lecture. Any questions? Yes.
A small question. So in your main result 3,
yes,
why you only state the result for dimension 2 and 3?
Yeah. So can you show me the slides? Can I see the slides? Okay, let me answer your question. So that is because like we are considering the case on the torus, because for example for Navier-Stokes you need to consider the constant solution constant in V, so that would be, you have to be in torus, otherwise you're not in L1. Now torus, there is some technical difficulties that we are facing when we try to get to dimensions 4 and higher. We believe it can be done, but it will kind of much more complicate our proof, so we choose to state the theorem in 2 and 3.
Okay, thank you. Yeah.
I have one question. So you mentioned, it's already the alpha equals log n. It's a remarkable advance, but you mentioned this, future that alpha could maybe a power of log or maybe a power of n. So that is far away, but still, is there an obstruction before n to the 1/3, before you get to the hard sphere regime? Like how far could you imagine alpha could go?
Yeah, so without proof, we cannot go beyond the log-log.
Sure,
but
what?
I think a single log might be possible, but I don't know. Like maybe the best, maybe the best you can dream is a small, like a constant power, but I don't think you can go beyond that. That's my guess.
But is there an obstruction that you know of before 1/3, right? So 1/3 cannot be achieved, but is there an can you say that, 1/4?
Okay, so I think, okay, so for example, in the wave turbulence setting, so if you work with this KZ spectrum, which is inverse power law, then, I mean, I have heard a talk in one of our earlier lectures at Simon's Collaboration that if you really get to, power law timescales, then you might see, extra terms which are vanishing in the original calculation that doesn't vanish when you get to longer times. I think at least for some power law, you are going to see those extra terms, and those extra terms will certainly bring at least correction terms to the wave equation, which we don't know.
Okay, thank you. Okay, we have time for one more question.
Yeah, so I'm not a mathematician, I'm a physicist, so I want to ask a physical question. So in your derivation, in the hydrodynamic limit, usually for physics, we consider it's like out of equilibrium. So in your Boltzmann equation, you mentioned there are some temperatures. When you use this formulation of the temperature, you assume it's equilibrium or it's out of equilibrium?
It's, I think these things are the local equilibrium, local Maxwellian.
So the temperature is a function of this position?
Function of x, yeah.
Okay, thank you.
Okay, let's thank the speaker again for an exciting talk.
请各位移步至1楼，乘坐大巴前往晚宴地点。另外，请将。